Okay, so it's 1 o'clock, so let's start. Good afternoon, and welcome to the international workshop on integration of simulation data learning and beyond. And it's also the 45th ASE seminar of the Information Technology Center of the University of Tokyo. And my name is Kengo Nakajima, and I'd like to overview the project and also this seminar. So first of all, I would like to thank all sponsors, JSPS, NEDO, and the JHPCN, and also Information Technology Center who are giving us this facility for conference. And this is the overview. So I start from the idea and some applications and some future issues and summary. So this is the history of the University of Tokyo's Supercomputer Center. And so we have nearly 3,000 users, and we are operating 2 big systems. So each one has a 6-year lifetime. And so this is shared by the Japanese researchers. And so more than 55% of the users are from outside of the University of Tokyo. And recently, we have new systems with green tags with GPUs, so accelerators. So this is a research area based on the machine hours last year. And so blue part is general purpose CPU, and green part is GPU cluster. Oops. Okay. And you can see engineering, earth and space science, materials science, and energy physics are very traditional area for the computer science and engineering. But you can see in the case of the GPU cluster, we have different colors, AI or bioinformatics or data analytics. So as you know, supercomputing is changing, and we have various types of workloads. So in addition to the traditional computer science and engineering simulations, we have a new users and area of research, such as the big data analytics, AI, machine learning. So we thought that the integration of simulation, data, and learning, we call this S plus D plus L. So this is very important towards Society 5.0. It's a human-centered society proposed by Japanese government by integration of cyberspace and physical space. And we started the BDEC project. BDEC stands for the Big Data and Extreme Computing. And we constructed the platform for integration of S plus D plus L. So in our case, we are focusing on these simulations. Okay? So this idea is AI for HPC or AI for science. Data and learning are supporting science. So this plan started at 2015. So we still BDEC run. So operation started 2 years ago. So this is our first BDEC system. It's a platform for integration of S plus D plus L. It's a Fujitsu system. Total peak performance is 33 petaflops and 8.4 petabyte per sec aggregated memory bandwidth. So we have 2 types of node groups. One is a simulation node groups called Odyssey, based on the Fujitsu's Prime HPC FX1000. It's a ARM AS64FX. It's a commercial version of the Fugaku supercomputers, and we have more than 7,600 nodes. And so, yes. And another part is called data learning node, Aquarius. It's for the data analytics and AI machine learning workload. It consists of the Intel Xeon Ice Lake and NVIDIA A100 Tensor Core GPUs. Totally, we have 45 nodes and 360 A100 GPUs. Some of these parts are connected to the external resources directly. So this is how we utilize this system. So basically, so in the case of the nonlinear simulations, we need a lot of parameter studies. So we apply the data analytics and machine learning to optimize the models and parameters to accelerate this cycle. So this is the last 2 years pie chart, which I showed before. And this one is, so this 6 months from April to the end of September. So you can see a lot of AI workload here. So it's mainly for the very special project for the large language model. So that's why we have more than 25% of usage for this kind of research area. And also we have increasing usage for the bioinformatics, such as genome analytics or medical image recognition by machine learning and data analytics. Okay, so this is the hardware, and we are also developing the software. It's called the H3 Open BDEC. It's a software platform for integration of S plus D plus S on BDEC systems, such as with BDEC 01. So it's supported by Japanese government since 2019. And so this fiscal year, and in the end of next March is final year. So today is a workshop of this project. And the leading PI is myself, and the total budget is $1.4 million US. It's not a so big project. So these are the core PIs of this project, and mostly, so they are the speakers of today's. And we also have the former postdocs, so they are also the speakers of today's, Dr. Kawai and Dr. Shiba. And also we have many contributors and collaborators from, so including industry. And so this is a part of the international collaborators. And so fortunately, we have two international speakers on site. So Richard Buduk and Shin Chai from so USA and Norway. Okay, so we have three innovations for this platform. One is new principles for numerical analysis by adaptive precision, automatic tuning, and accuracy verification. So we have 4 speakers related to this area. Okay, so I'll talk about a little bit more about this part. Mostly, scientific computing has been conducted using double precision, FP64. But sometimes problems can be solved by FP32 or lower precisions. And generally, lower precision may save time, energy, and memory. And the idea of the approximate computing was originally for image recognition, etc., where accuracy is not necessarily required. But recently, it's also applied to numerical computations. Computations by lower precisions and by mixed precisions may provide results with less accuracy. I'll show you some very preliminary examples. So it's a steady 3D heat conduction by finite volume method. It's a 7-point stencil. And we have inserted different material properties, and we have a little bit heterogeneous material property. The quotient matrix is a SPD, so therefore we can apply the ICCG solver. Okay, so in the next page, I show some result. And so in this type of geometry. And so this axis shows a ratio of the lambda 1 and lambda 2 from the uniform material property to the ratio is 1 million. And it's a ratio of the FP32 and FP64, single precision and double precisions. And black circles are number of iterations, and white triangles are computation time for ICCG solver. So this ratio shows if it's more than 1, FP32 is slower. And if less than 1, FP32 is faster. And you can see we have additional iterations if you apply the full FP32, so roughly 20%. But even if we have more iterations, we can save the time for computations. So it's less than half. But if you increase this ratio, it's more ill conditioned. So in this case, number of iterations are increasing like this. And you can see in this case, so single precision is rather slower. Okay. So this is power consumption and energy consumption for the CPU part and memory part. Power consumption is almost same, but energy consumption is it's computation time. Okay, and you can save the energy consumption using this single precision in certain cases. So in this type of case, accuracy verification is very important, especially for computation with lower and mixed precisions. a lot of methods for accuracy verification have been developed for problems with dense matrices, but very few examples for sparse or H matrices. And generally speaking, processes for accuracy verification is very expensive. So we need a sophisticated method, and automatic selection of the optimum precision by technology of automatic tuning is very important. And my colleague, Professor Ogita, developed a new method for accuracy verification of the sparse linear solvers, and he will talk about that later. So we have three related talks in this part. And we also develop intermediate precision, FP21 and FP42. So this is talked by Dr. Kawai in later stage. Okay, second innovation is integration of S plus D plus L by some combination of the machine learning and simulations. Okay, so we have three related talks. And the first one, the prediction of the simulation by machine learning and the convolutional neural network. So this will be done by Takashi Shimokabe later. And we also developed a new method using graph neural networks for the molecular dynamics. And this is talked by Professor Shiba. Okay, third part is the software and utilities for heterogeneous environment, such as the Wisteria BDEX01. So we have two talks. Okay. And as you know, so Wisteria BDEX01 is the first really heterogeneous system in the world. So we have a totally different architectures. This one is ARM, and this one is Intel Xeon plus NVIDIA GPUs. And if you want to combining these two parts, so single MPI job over Odyssey and Aquarius is impossible. But fortunately, so they are connected through InfiniBand EDR with 2 terabyte per second. It's a very rich network. And we developed a new library on this InfiniBand called H3 OpenSys WaitIO socket. It's a library for interprocess communication, so for this type of heterogeneous environment. So details will be given by Professor Sumimoto later in this afternoon. Okay, so I will show you some examples, okay, applications. So actually, seismic propagation simulation is one of the motivation for development of the such framework, both for the hardware and software. So this is a 3D earthquake simulation with real-time data observation and assimilation. So we try to combine the real-time observational data and simulation for the more accurate result. So as you know, earthquake simulation is always with uncertainty. So because we don't know the details of the underground. Okay? It's heterogeneous, random, and stochastic. And we have many fluctuations. Therefore, integration of simulation and observation is very important for this type of area. But so far, traditional simulations are just the so-called forward simulations. But recently, new types of the methods for simulations combined with data simulation, real-time observation is under development. So it's a forecast by simulations and correction by data simulation. It's proposed by my colleague, Professor Kurumura from the Earthquake Research Institute of University of Tokyo. Simulation itself is a very simple, 3D finite difference. It's a fourth order, but so it's very simple model and explicit time matching. And we try to utilize observational data. Okay. So JDXNet is a real-time sharing of the seismic observation in Japan. And we can share the observational data over the more than 2,000 points in Japan, real-time through SciNet. It's an academic network in Japan. And the total amount of the data is roughly 400 or 500 gigabytes per day. Okay. And so it's including some observational data by satellite. Traditional simulation is so this one, pure simulation. we estimate some source term at the epicenter, and we do some wave propagation simulations. But if you estimate a wrong initial conditions, we have a wrong answer. So our new method is a assimilation plus simulations. So we generate the initial condition by the observational data. So these yellow triangles show the observational points. By interpolation or extrapolation of these data, we generate the initial conditions. And also during the computations, we update the computational result using these observational data, using the real-time observation. So this is how we utilize this A plus S, assimilation plus simulations. So we start from assimilation plus simulations. And so at certain point, we switch to the pure simulation. So just doing the simulations. So this is the system we constructed on the Wisteria BDX01. So we have a external server or JDXNet, and we can get the observational data. So we import that data to the Aquarius GPU part and applying the filtering. And they send to that result to this Odyssey part. And they are doing assimilation and simulation. And finally, visualization is coming back to this part, and so done by this part. So this is the interface between the Aquarius and Odyssey for sending the filtered data. And the details will be done by, again, so Professor Sumimoto later. I skip the detail here. Okay, so this is examples based on the Ohu Niigata 2007 magnitude 60.6 earthquake. And so we have nearly 1 billion of meshes. And so this is a target area, and we have more than nearly 350 observational point. It's a green squares. And this is the epicenter, and this is the Tokyo area. So we have a 200-kilometer distance between these parts. Okay, so this is one of the results, and this is the epicenter, and this is the Tokyo. And this is the observation at this Tokyo area, and these are the computational results for this part, okay, Tokyo area. So this line shows the switching time from A plus S to pure simulations. And you can see after 50 seconds, you can get a very accurate solution, which agrees with the observational data well. Okay, so this type of system is an accurate prediction for the seismic wave propagation with real-time data observation and assimilation. So this is very useful for the emergency information for safer evacuation. So actually, this type of the computation can be done very fast, and we can utilize this type of the simulation for the real-time emergency information. For example, so if you apply nearly 2,000 nodes of the Odyssey, you can solve the problem for the 240 seconds in roughly 22 seconds. So yeah, 10 times faster, okay? And it's possible. But this type of event is not so often. And so we are trying to utilize this type of system for another way. So as I mentioned, 3D underground model is not so known. And every time if we have a small earthquakes, we can utilize that data to construct a more accurate and detailed 3D underground model. And we are trying to utilize some techniques for the data assimilation and machine learning for improvement of these. Okay, so this part is now done by Professor Nagao, and he will talk about this type of topics later. Okay, so we are also applying this type of the systems for the outreach. So as you know, we have a lot of earthquakes in Japan, and so this is a very important facility to learn about how the seismic wave propagate. Okay. So we developed a wave-based system on the supercomputers, and so users can easily access from the web browser to run the supercomputers. Okay. I skipped the detail here. Okay, so another example is atmospheric computations. And we also develop a multi-physics coupler. Traditional coupler is a weak coupling tool of the multiple applications, usually two, okay? And each application does a single computations, ocean atmosphere and fluid structure. And in the previous project, we developed a very nice coupler for coupling the ocean and atmosphere. And we solved the problem for the super El Nino on K computer. It's 6 years ago. But our current coupler is an extended version of this type of the multi-physics coupler for coupling simulation workload and machine learning workload on Odyssey and Aquarius through this network. Okay, so details will be done by Dr. Yashiro later. And initial coupler was developed for this MPI homogeneous environment. But last year, we developed a new coupler combined with the WaitIO library, which I mentioned. And we can do that on the heterogeneous environment now. Okay, so I skipped the detail of this part. And so this is a detailed cloud model. And in this type of the simulation, we combined with a coarser model. So this part is called parameterization. So our motivation is to replace this part with AI, okay? And so we run this part on Odyssey and run this part on Aquarius. Then we can reduce this part. Okay, so I skip this part, and details will be talked by Dr. Yashiro later. Okay, so in order to run this type of workload, so it's very difficult. Okay, and so now Odyssey part is not so crowded, and Aquarius part, GPU cluster, is very crowded. And we are now assigning the one node of Aquarius for this type of workload. And the two separate jobs should be submitted. And if both jobs grab resources, execution starts. So actually, more flexible and complicated policy needed, but now it's running on this way. So details will be also talked by Professor Sumimoto later. Okay, so I'll show you some examples of the international and domestic collaborations. And since we started operation of this type of the system, we have several new such workloads. So one example is the uncertainty quantification of the extreme weather prediction. It's by Professor Sawada from University of Tokyo. So next one is a very interesting one. It's a joint work with Riken and Osaka University and Tohoku University. So it's a prediction of the marine ecosystem. So we are combining the very detailed ocean simulation with some ocean observation. So next one is an international project which started this fiscal year. And it's a joint work of the Japanese institute. So basically it's our institute. And also collaboration with some URI, some Croatian institute, and FAU Erlangen, and CA in France. So we have several target applications. One is regional earth science systems, and some eigensolvers, and the brain simulations, and also some very important simulations for COVID-19. It's a combination of the density function theory computations and molecular dynamics. And this is also the very old collaboration, and so with a similar research laboratory for the cardiac electrophysiology. Okay, so this is a current result, and I'll talk about a little bit about our future. So basically, so anything is possible with WaitIO library. So even if you have a very heterogeneous environment, such as ARM, x86, and many kinds of the GPUs. And so we are now introducing a new system called OFP2, bit open just 3 weeks ago, and Fujitsu was awarded. And it's a heterogeneous system consisting of the CPU part and the GPU part. And the CPU part is based on the Intel Xeon Max with a high bandwidth memory. It's called Sapphire Rapids. Okay? And we had a very small portion, only 190 nodes and 1.3 petaflops. And the larger part is a Group B. It's NVIDIA's GH200. It's a so-called Grace Hopper superchip. It's based on the H100. And we have more than 1,000 GPUs. Okay? And so we are combining these two systems. So basically, all nodes are connected with a full bisection bandwidth, but operation will be separated. Okay? And operation starts in January 2025. And so WaitIO library will be adopted for communication between these Group A and Group B. Okay. So this is a near future plan. And also we can extend this idea to other types of devices, such as these AI chips or quantum computer. And we are now starting the new project. So for the system software for quantum HPC hybrid environment. So here, quantum computers is treated as accelerator for the supercomputers. Okay, and we are developing a system software for efficient use of this hybrid environment. One is a cost scheduler, and another one is a communication library. So this idea is extended of the WaitIO library, which I mentioned before. So innovations, so this is the world's first attempt to link multiple supercomputers and quantum computers installed at different sites in real time. Fortunately, or unfortunately, in Japan, generally quantum computers and supercomputers are located in different places. Therefore, we need to connect these through the external network. Okay. And in particular, by using multiple quantum computers simultaneously, so it is possible to form a vertical quantum computer with a higher processing capacity. Actually, so I thought this is a very nice idea. But so 2 weeks ago, there's a SC23 in Denver, and many people are thinking about the same thing all over the world. So I think it's a very straightforward, natural idea. But so now, so we are developing this type of idea. And this idea can be extended to any types of the systems. So we are starting this project as a 5-year project from now. And so, yeah, let's see what will happen. Okay, so I just briefly overview of our project, including hardware and software and collaborations and the new challenges towards quantum computing. So this is a summary of our activities. We have nearly 60 journal papers and proceedings peer-reviewed, and almost 90 presentations, plus invited talks, and 1 book. So we have 2 awards, 1 best paper, and my personal award, but it's mainly focusing on this project. And this fiscal year, after 2023, I have a lot of invited talks and keynote talks on these issues. Okay, and the next year we have a WCCM 2024. It's a computer mechanics conference, and we also have another invited talks. Okay, so it's very difficult to define the final goal. But in the proposal, I stated this sentence in Japanese. We aim to reduce the amount of the computations and power consumption by more than 10 times while maintaining the same accuracy as conventional methods in multi-level simulation that integrates S plus T plus N. At that time, we thought if we combine the mixed precision, machine learning, and also heterogeneous computing, it was possible. Okay, and somehow we attained this initial target. And in the end of this workshop today, so I will make the final self-evaluation. We still have 4 months left, but so I'll talk about that. So yeah, through the after the all presentations by my colleagues. Okay, so this is the program today because it's a half day, so very crowded workshop. Therefore, each speaker has only 15 minutes. Okay. Yeah, and we have very excellent invited speakers, Richard Buduk from Georgia Institute of Technology, USA, and Dr. Shin Chai from a similar research laboratory, Norway. Okay, thank you very much for your attention. And any questions? Okay, so I think it's almost time. Okay, so this is a program of the first half. So as you see, so each has only 15 minutes. And I asked each speaker summarize their talk in 13 to 14 minutes. And we can allow the one quick question. And you can see we have a discussion time after the keynote talk by Rich. And we can make a more detailed discussions here. Okay. So if you have no questions, so let's move to the next speaker, my colleague Takeshi Iwashita from Hokkaido University and Kyoto University. So are you ready?
Yes. So I wish to my slides. So can I start my talk?
Yes, go ahead.
Oh, okay. So thank you very much for inviting me to this workshop. And today I'd like to introduce some research results conducted by Hokkaido University subgroup in Kengo's project. So, and most of the results were done by students of Hokkaido University and Professor Fukaya and me. So, and one of our topics of the research is mixed precision computing. So, and we first developed a mixed precision version of the GMS-M solver, and this solver is So this solver is based on the iterative refinement method, and M-step low precision GMS solver is used in the inner iteration. And in the outer iteration, the residual vector is calculated using the conventional FP64, and the convergence of the relative residual norm is checked by using the FP64. Thus, the accuracy of the solution is the same as that of the conventional FP64-based GMS solver. And actually, so we conducted the numerical results, and we showed the effectiveness of this research, the approach. And if you are interested in this topic, so please refer to this paper. And next, so we also conducting the research similar to the first one. So in this case, so we use the low precision biases type method in iterative refined method. And usually we think that the Lanczos type method is not suitable for the inner iteration of the iterative refinement framework. But anyway, so we tried to examine the method, and we got some good results for some data sets. So it is not perfect, but the result shows some potential of this approach, including the Lanczos type method. So, and in near future, so the result will be published in a journal. So if you are interested in this topic, so please read our paper. So next, so we also conducting some research on the H matrix method. So in this method, so we introduced low precision computing to the submatrices, low rank submatrices, and we verified the method in the analysis of the boundary element method, and we got some good results. So, and we published the result in the HPC Asia 22, and I think it is one of early work of the H matrix using the low precision computing. So, and if you are interested in the details, so please read this paper. And we also conducted research about the integer arithmetic. And integer arithmetic-based preconditional GM solver was developed in our group. And the solver is based on the iterative find method. And only integer arithmetic are used in the inner iteration. And of course, the convergence will decline compared with FP64 GMRS, but it is very marginally. So, and we reported the result in the Scale 2020. And now, so we are conducting the research on the this type of method using the multi-grid preconditioning. And in the near future, so we will report the result of the MG GMS method using the only integer arithmetic. So this solver is also based on the iterative refinement framework. And the second topics of our group is IRU type precondition technique for the SIMD vectorization. And we propose the hierarchical block multiple ordering method. And this proposed ordering method attains the same convergence rate as the block multiple ordering method. And the block multiple ordering method currently often used in the HPCG benchmark. And this new ordering also guarantees the same convergence rate to the block multiple ordering. And we got some good results for this new ordering on the CPU. And currently, so we are developing the GPU version of the IRU type solver using this hierarchical block multiple ordering. So in near future, so we will report the result in a conference or in a journal. So this is another research result about the IRU preconditioning. So a new failing strategy was proposed for the IRU preconditioning. And in this method, so non-zero blocks are defined and all three ins in a non-zero block are permitted in a factorization. And in this case, the forward and the backward substitutions consist of a small dense matrix operation, and it is very suitable for the SIMD vectorization. And we got some good results in the numerical test using the matrices downloaded from the sweet space matrices. So, and if you are interested in this topic, so please read this journal. So it was already published. Okay, and the third research topics of our research group is GPU-oriented preconditioners. And we proposed a new AIM, so approximate inverse preconditioner. And modification of the AIM algorithm was presented. Because the construction phase of AIM preconditioner was usually very time-consuming, this preconditioner is very good for the GPU computing in the iteration phase, but the construction phase is usually done on CPU, but it costs very much. So, and we developed a new strategy for a dropping rule of the construction of the preconditioner, and we can successfully reduce the time for the construction of the preconditional matrix. And in this case, how to say? So we have to consider the side effect of the dropping rule, the change in the dropping rule. But in the GPU for the iteration phase, so we can get the comparable convergence, right? Compared with the usual CPU-based normal A in precondition. So, and the result was already published in this paper. So if you are interested in this topic, so please read this paper. And finally, so I'd like to introduce one more research. The topic is the speed up of the convergence of the sparse linear iterative solver. And in this research, so we use the two types of method to accelerate the convergence. So one is the subspace correction method, and the second one is the deflation method. So, and in these techniques, the deflation vectors or the definition of the subspace is very important to accelerate the convergence, right, of the iterative solver. And if you can identify the eigenvectors corresponding to the small eigenvalues, and you use these vectors for the deflation vectors or the subspace correction. In this case, we can get the acceleration of the convergence rate. But it's usually difficult to identify the eigenvectors corresponding to the small eigenvalues. And the key idea is here. So there's no free lunch. So we focus on this situation. So that we focus on the series of solution of the linear systems. And in the first solution step, so we got some information about the eigenvectors with small eigenvalues. And then the following solution step, so we use these information for the deflation method or subspace correction method. So, and we sample the approximation solution vectors in the solution step. This is the first solution step. And we construct the subspace to identify the eigenvectors or with small eigenvalues. And using these vectors, so we accelerate the following solution steps using the deflation method or subspace correction methods. So I would like to show some results. So in this case, this figure shows a convergence acceleration by using the subspace correction preconditioning, and this is based on the deflation method. And in these cases, both cases, so we can get a significant convergence acceleration. So this is a normal ICCG method in the first solution step. But if we use the information obtained in the first solution step, so we can accelerate the these convergence of the following solution steps. So, and in some cases, we can get a 4 times speed up of the convergence compared with the normal ICCG method. And from the viewpoint of the computational time, in some cases, so we can get the 3 times the speed up compared with the ICCG method. So, and if you are interested in this research topic, so please read this paper published in the numerical linear algebra application in this year. So thank you very much for your attention. So if you are interested in our research topics, so please make contact to me. So I would like to discuss it with you. It's very honor and happy for me. Thank you very much.
Thank you very much. So any quick question? No questions? Okay, thank you very much again. And let's do the next talk by Takahiro Katagiri from Nagoya University.
Thank you.
Thank you very much.
Okay, so let's start. So my name is Takahiro Katagiri from the Nagoya University. Today I'd like to talk about explaining AI for the auto-tuning through sparse matrix image information. So in this project, we have two roughly aim. So first one is that the development of the AT framework for the mixed precision computation and power consumption. So I have developed some directive-based AT language named the PPOpenT. So we extend the new function to match this requirement, but today I'd like to skip this matter. So, very short time presentation. So first one is, I think, very important thing. So development the AT facility with CII. So we can adapt the auto tuning facility by using the deep learning technology. But so I think that not so much study is done by using the adapting the XAI. That means that we have easily make a AI model, but so nobody verified. So I think really, really important thing. So in this talk, I will focus on these topics. So this is the outline. So I'd like to see the background. So you see, utilizing unverified AI prediction result to contribute to various social problems, you know. So human sense verification is very essential. So on the other hand, to maximize the production cost, there is extensive research in the field of software auto tuning technology. So that's why we are focused on this technology. And in this field, so the integration of the AI into AT is very important task. So we are now trying to do this. So in this situation, so it will be crucial to vary the explainability of AI by tuning performance parameters, even in the numerical libraries. So very important things. So some people say that this is the scientific XAI, is XAI, but I have never seen this detailed analysis paper. So I roughly try to this topic in this project. So explainable AI is categorized into two things. First thing is that explainability, that is the AI technology for the reason prediction to be understood by the human sense. So famous tool is known as the Lime and Sharp. Maybe you are using it. And another thing, the interpretability. So technology to show a process prediction by analyzing the inner structure. So that is making a decision tree or something like that. So in this study, we focus on the explainability. So that is by using the Lime and Sharp tools to explain the making the to check the auto-generated AI models. So in this talk, so we focus on Sharp. So Sharp is a Sharpley additive explanation. So Sharp is based on the Sharpley values. So this kind of theory is a cooperative game. So that means that a very reasonable background in viewpoint of the theory. The one drawback is that to calculate the Shapley value, it costs so much. So in the strict calculation, so that in the recently, so many roughly calculate the Shapley value method present shown here. So we are now using the very easy to use to calculate the Shapley value by using the through the Sharp tool in there. So anyway, so we are using a Sharp tool in here. So I'd like to show you the one example. So PICG, ICCG parameter tuning case. So maybe you know the PICG algorithm well, but I roughly explain this one. So in this numerical algorithm, we use the incomplete Cholesky factorization to solve this linear equation system. And so you know the very trade-off is there. So we take the very, the filling depth is long. So that means that includes the memory amount and the computational complexity going up, but the precondition going strong. That means that it reduces the iteration time. But so with respect to the total execution time, so that it's not so good. So we need some trade-off between the computation time and memory amount and total execution time. So we have somehow parameters. So for the preconditional. So in this case, IC preconditional with the threshold is use so two parameters in there. One is the maximum filling level M, and another one the threshold value T. So by setting these parameters, we can get nice preconditionals and also very critical parameters. So the M is adapting to make auto tuning, automate setting for these two parameters. So auto tuning method, we have developed some special techniques by using the information of the sparse matrix figure. So this is an example. So input, we use this information, sparse matrix feature image. And the explainable variables, in this case, the maximum filling level and the threshold is input. So output is this is the execution time of the ICCG method in here. And so with this input and output, so we have learning with CNN like this way. And this is the learning setting. So that's easy. But so the problem is that this model is what is said reasonable or not. So actually, so we have setting data set. Well, this is come from the Professor Nakajima's data set. So Professor Nakajima mentioned that I forgot. So there are 3 layers and lambda 1, lambda 2, lambda 2, lambda 1, and the medium density changing so that we can change the condition number. So in this case, it's 19 kinds. And we take the 3 kind of sizing here. And so we choose the maximum filling level, the 3 kinds, 0, 1, 2. And the threshold value is a set this range, about almost 200 kinds. So training data is not small. So the training data is almost 40,000 kinds for each size. And the testing data is 10,000 kinds each size. So we can get, we use this data set for learning. So this is the result of the auto-generated model. So with this data set. So this is the estimated maximum predicted time, and this is the absolute error. So that means that it's prediction and measured execution time, absolute error. So with this point, so we have less than 10%. That means a very good model in this case. So in usual thinking, so this is a good model, but not verified. So what happens in viewpoint of the XAI? This is the point in this presentation. So we have adapted the sharp in this with this model. So this is the result. So this is kind of difficult to read. X-axis shows the tolerance of fillings. So if the tolerance of fillings are large, so the number of fillings is smaller. So that's small memory amount is a weaker precondition, something like that. And y-axis shows the Shapley value. So if the Shapley value lower, so has the effect of the decreasing execution time. That means that it tends to speed up in this case. So with this explanation, so as a result is kind of reasonable because tolerance of filling the smaller, so the max filling the level 2, so is going to faster. So that is a very nice matches for the theory of this algorithms. So it's good for max filling level 2, but so with respect to max filling level 0 and 1 in here is something strange. So this one and this one and this one. This is because data is no filling at less than the filling level 1. in the training data. The execution time does not depend on the threshold in the data, but the explanation is somehow changing. So that means that not reasonable explanation. So this is the kind of problem, the explainability. So we have checked this one. So in viewpoint of data and the algorithm. So one thing is that so poor explainability, encoding system is not so good. So the one-hop encoding, like this one, is a very known method. So by adapting the one-hop method, so this situation is changed. So this is our experiment. So by adapting the one-hot encoding, so the model is very improved. And explanation is also changed. I will show you later. In that way, so the auto-generated model is very improved, maybe 40% map. So that is a very good things to checking the experiment. Anyway, so we get a more good model by using this 180. So by again, so we check the explainability through the sharp, so that in that case is also flat one, so that makes sense. So that good things. So this one is a very good things. Good things for adapting XAI. But there is another story. So with respect to the data and the algorithm implementation, so we found a bug in this part. So this is a kind of something strange. So situation is still in there. So that so we found the bug. So that is a very what is the additional merit for adopting the XAI. So we check the algorithm meaning that the result of the XAI thing. So it's very important. So this is what is another merit anyway. So conclusion is that so I think the explainable AI is also a very important tool, even in the auto-tuning in the numerical library, and by adapting in case of the adapting the deep learning case. And we also thinking about this all concern, but very interesting approach. So if we adapt the XAI, we found a very weak strong factor. So that means that we need to reinforce reinforcement learning should be done in that explainable variable. So we found a very weak factor, so we may reduce that these what to say the parameter tuning in that variable. Anyway, so we use that some information of through the XAI tool. Another thing is that we try to mix precision auto-tuning by using deep learning. That means that the automatic selection of the double and single computation in the ICCG. It may be possible, but we are now trying to these things for auto-tuning. So thank you very much for your attention.
Okay, thank you very much.
Thank you.
So let's move to the next talk. Okay, so next speaker is Professor Hiromichi Nagao from Earthquake Research Institute from University of Tokyo.
Good afternoon, everyone. So I'm Hiromichi Nagao, Earthquake Research Institute at the University of Tokyo. First of all, I would like to thank the organizers and organizers to give me such a great opportunity to introduce our lab research. So this is my CV. But properly it's hard to see. Okay, so I graduated from Kyoto University and I studied geomagnetism at the time. I developed a Kalman filter algorithm to detect very in the time series data. I was collaborating with the Institute of Statistical Mathematics to develop the method. So 10 years ago, I came to the current institute as an associate professor, and my interest is in the developing statistical and information science methods beneficial to science module. So this is the outline of today's talk. I will talk about the 3 topics in a limited time. So first one is the development of algorithm of data assimilation. The second one is the development of a deep learning model to detect seismic waves from the continuous waveform data. The third one is the also the development of the deep learning model to detect low frequency tremors in historical seismic paper records. So the first topic is related to the data assimilation. So data assimilation is a computational technique to integrate numerical simulation models, and observation data in the framework of Bayesian statistics. The data assimilation plays an important role, especially in the weather forecasting. So the weather forecasting you see every day is the result of data assimilation computation. So of course, the integration of simulations and observation data is very important, not only in the weather forecasting, but also seismology and material sciences and of other fields. So data assimilation technique is nowadays widely used in the various fields of science. So there are many techniques in data assimilation, and so we study especially four-dimensional variation method or adjoint method in recent years. So adjoint method is used especially in the weather forecasting. So this is the simulation model. This is a simulation model, and we assume a autonomous system for the simulation model. And this is this equation indicates the observation model, which compares the simulation result and observation data. Okay, so the adjoint method. The adjoint method optimizes the initial condition with respect to the observation data. So, so the adjoint method searches the best initial condition, which that maximizes the posterior distribution or minimizes the cost function. Cost function is the negative log of the posterior distribution. So the key equation in the adjoint method is the adjoint equations. Adjoint equations can be derived from the cost function using the variation method. Now, the conventional adjoint method can only searches the optimal solution that maximizes the posterior distribution. So the conventional method never evaluates its uncertainty. So in 2016, we developed a new algorithm to quantify the uncertainty in the estimated optimal solution. So we can add such an error bar in the solution. So of course, such an uncertainty information is very variable in the various field of science. So, for example, such uncertainty information can give feedback to the experimental or observation design. So this is a concrete algorithm to how to quantify the uncertainty. So the key technique in the uncertainty quantification is the second-order adjoint method, which can be written as in this equation. So this method, this second-order adjoint method, the input to the method, is the vector R, and the second-order adjoint method outputs the product of Hessian matrix and the input vector without knowing the Hessian matrix. This is the key point. So now I omit the detailed algorithm of this method. So the second-order adjoint method makes makes it possible to compute the limited number of diagonal elements in the Hessian inverse matrix. This is the key point. And now we applied our uncertainty qualification method to the seismological problem, seismological issues. So Dr. Ito, who is the assistant professor of our institute, developed this algorithm and then applied to the seismological issue called the slow earthquakes. So, slow earthquakes is a hot topic in the modern seismology, which is much different type from the conventional earthquakes. So Dr. Ito and I, we show the uncertainty can be quantified for the precaution parameters on the fault, where the earthquakes take place. Okay, now then we are trying to apply our method to the issue of seismic wave propagation. So so the simulation of seismic wave propagation is very massive. So the we can apply it to the 3D problem, but now but we have applied our method to the problem in the two-dimensional cases. So now we solved this wave equation in the 2D media, and we assume the 2D media for the underground structure, and we show that our proposed method can correctly or accurately evaluate the uncertainties for the underground structure parameters. Okay. Okay, then the next, I move to the next topic. The second topic is the development of the deep learning model to detect the seismic waves from the continuous data. So there are many seismic observatories in and around Japan. There are more than 2,000 such observatories are shown in this map. So now we have more than 30,000 earthquake events are taking place in around Japan. More than 3,000 earthquakes in a month are taking place in around Japan. So okay, this is the actual seismic continuous data. So we have to detect P and S waves from the continuous data repeatedly. So we call this seismic wave picking, like this. Okay, here is the P wave, and here is the S wave. So of course, this seismic wave picking should be done automatically. So in recent 30 or 40 years, such seismic wave picking is carried out by using the statistics method using the AR model or auto-regressive model. But so the amount of seismic data are greatly increasing. So such conventional method for seismic wave picking should be replaced with AI technology. Okay, also okay. So now a new era is coming in seismology through the integration of AI technique. So in 2018, the first AI technique to detect seismic waves, or the seismic wave picking. It's released. It's published by the Dr. Ross, who is a Caltech, assistant professor of Caltech. This method is called the GPD method. The GPD method detects the seismic waves, classifying into the P wave, S wave, and noise. So this is a great method, and nowadays the number of seismic wave picking methods using AI deep learning methods are released, and we also develop deep learning method for the seismic wave picking. So Dr. Tokuda and I published a paper which proposed upgraded GPD method. So the conventional GPD method applies the deep learning model to the seismic waveform in 4 seconds. But the disadvantage in the conventional GPD method is too sensitive in the seismic wave detection. Too sensitive. So in order to improve that disadvantage, we proposed applying not only the 4-second time window, but also apply to the short time window, and merge the result and merge the result. So our method performs much better than the conventional GPD method and other deep learning methods. Okay. And then I move to the third topic. So the third topic is the development of the deep learning model to detect low frequency tremors or slow earthquakes. So the slow earthquakes or low frequency tremors are discovered in 2002 by Professor Obara, who is a professor of our institute. So this is the hot topic in the modern seismology. So the slow earthquakes, the low frequency tremors, seem like a noise, not much different from the ordinary earthquakes. So owing to the dense seismic observation array, so Obara can discover the slow earthquakes or low frequency tremors. So of course, but such a slow earthquakes or low frequency tremors of course must have taken place more than 20 years ago. So of course 40 or 50 years ago, or 100 years ago. So our idea is to detect such low frequency tremors in the historical seismic record. This is the photo of a historical seismogram. So we said Ogihara's mechanical seismogram. So the classical old type of seismograph draw a waveform directly on the paper. So there are many historical paper records like this in our institute. So we develop a convolutional neural network to detect low frequency tremor from such a historical paper records. Now this is this shows the strategy to develop for development of a CNN model. So this is the convolutional neural network we developed, and we use the modern we use the images converted from modern seismic waveforms for the learning data set. So okay, we generated a number of learning data sets from the modern seismic waveform data, converting the images, and then we apply we apply the trained CNN model to the practical paper records, and we try to detect the low frequency tremors. Okay, this is the result, application example. So this is the example of success cases. So this is the actual paper record. You can see the such black bands here and here. This is the low frequency tremors. Our model successfully detects such low frequency tremors, and so our method found unknown low frequency tremors that took place more than 50 years ago. But our model, there were some examples of unsuccessful cases. So like this. So we can see here and here a low frequency tremor, but our method failed to detect. This result is a clear failure case. So we investigated the cause. So we found that the thickness of the pen is much different between the successful and unsuccessful cases. When the pen thickness is thin, our model can successfully detect the low frequency tremors. But when the pen thickness pen was thick, so our methods was unsuccessful. So we studied that. We learned that the training data set is not sufficient in cases. So now we are considering the increase the learning data set, and we are considering to update our CNN model. Okay, now this study was published from the JGR, the journal called JGR, and if you are interested in, please refer to our paper. And this study is introduced in a newspaper in Japan in March. So if you're interested in our study, so please refer to the newspaper. Please refer to this newspaper. Okay. Now I conclude my presentation. This is a summary. And now, so our laboratory is carrying out a national project related to the integration of information science and seismology. So we published a newsletter and we constructed a website, and we released a promotion video like this. So if you're interested, so please accept here. So thank you for attention.
Thank you very much. So any quick question from the audience or online? Okay. Okay, thank you very much. Okay, so next talk is Takashi Shimokabe, is my colleague from Information Technology Center. And so please start if you are ready.
Thank you. And I'm Takashi Mukabe from the University of Tokyo. I will talk about the fast prediction method for the fluid simulation result using deep neural networks. So first of all, our group aim is accelerating the MD and the CFD, or predicting the MD or CFD result by using the new deep neural network. So in this talk, I'm focused on the CFD case, and the next section, the 4:35 p.m. Professor Shiba will provide the case of the molecular dynamics. So in this talk, the target is computer fluid dynamics, and this is an important application in the field of HPC. So CFD and the application is based on the many computation grid or mesh or particles, so that it is well known that the computation cost of CFD is relatively high. So and the CFD application require a lot of computational time. So in this project, so we are currently working on a project to develop the fast prediction method of the steady and unsteady flow simulations using the deep neural network DNN. So here is the basic idea of the DNN prediction of the flow. So first we perform the CFD simulation in a traditional way to generate the training data set, and in our research, we use the Lattice-Boltzmann method for these simulations. So once we have the data set, we build a network architecture based on the convolutional neural network, CNN, and we training it. So after training, we can use the trained neural network to predict the CFD simulation results. So the CNN may become the faster simulator. So first, the topic is I will show the case of the prediction of the steady flow. So in order to make the training data set, we perform the Lattice-Boltzmann method, the simulation using D2Q9 model with a Reynolds number of the 20. That is because the steady flow. So the fluid flows along the x-axis, and we place the random-sided cylinders and the polygons at the random locations. So since it is difficult to train the models using the large size data, so we clip the data with the size of the 256 and times the 128 from the original data. And we split about 60,000 data into training data set and the validation data set. And we use the signed distance function to represent the geometry, including the cylinders. So CDF provides a universal representation for the different geometry shapes and works efficiently with neural networks. And SDF provides a zero at the object surface and the positive distance in a fluid, and the negative distance is the inside the object. And here is the new network architecture, and the encoding part is shared by all dimensions, and the decoding part is different in each dimension. So the encoding part consists of the several convolution layers, and the decoding part consists of the several deconvolution layers. So we use the signed distance function and the boundary condition of the velocity as the input, and the signed distance function is used to represent geometry. So this model provides the velocity field as the output. So in order to improve the accuracy, the model provides the information of the location of the object as the mass. So here is the prediction result for the single domain. The left side of the figure, the CNN prediction and of the velocity fields, and the middle figure shows the LBM ground truth. So the right side of the figure, the difference between the CNN prediction and the LBM result. So as shown in the figure, and our model will predict the LBM ground truth and truth. And the running itself is done by placing the simple shapes such as cylinders and polygons. So here is we show the result of the prediction in a complex shape. And that means that not in the training. So you can see that is some of the curve object. So on the left is the prediction by the CNN, and the middle is the ground truth, and on the right side is error. So we can see that the CNN model predicts the result with the sufficient accuracy for the complex shapes. And in order to predict the result of the large size domain, so we propose the prediction method using the CNN and with the boundary exchange. In this method, so we decompose the large size of domain to the multiple subdomains, and we train a network model to predict the single domain result, and apply it to the decomposed subdomains to predict the simulation result in each subdomain. And in order to maintain the consistency between the value in the subdomains, so the boundary exchange between the neighbor subdomain is performed. So CNN and boundary exchange are performed iteratively until values converge. So here is the prediction result. It's using a result for the decomposed multiple domains. So the left side of the figure are the initial prediction by the CNN with an initial unknown boundary condition. So after CNN and the boundary exchange between the subdomains performed iteratively, the prediction value converged to reach the final prediction. This is the final prediction. So the right side of the figure is the LBM the ground truth. So that's shown in the figures. Also, there is a little difference, especially in the boundary region. The development method can accurately predict the value in almost all computational entire domain. Okay. And the topic 2, that in the case of the time-dependent flow. So for the time-dependent simulation predictions, so we treat the data as the 3-dimensional data. So 2 dimensions in the space and 1 dimension in time. So we use the 3-dimensional convolution neural network for this prediction. So the input data are the 3 frames at the 100-step interval in the LBM simulation with simulations. And the output is the prediction result, the next 3 frames. And here is the network architecture. This network also consists of the encoder part and the decoder part. So the encoding part consists of the several 3D convolution net layers, and the decoding part consists of the several 3D deconvolution layers. So we use the discrete velocity distribution function in the LBM with the signed distance function for the represent the geometry shape for the input. And this model provide the discrete velocity distribution function as the output. And also we use the skip connection that usually used in the unit, and also we apply the normalization to the input and output data to improve the accuracy. And also we use the loss function and based on the collision process in the LBM. So this slide shows the variable and the government equation of the lattice-Boltzmann method, and in our network architecture, so these the here. These discrete velocity distribution function directly use the input data instead of the flow field velocity. And in addition to the improve the prediction accuracy, the collision term that is here of the discrete velocity Boltzmann equation and used in as the loss function. And here is the how to predict the large simulation result. The prediction result of the large scale simulation require the prediction for the region beyond the size used in the training. So we apply the CNN inference, the partially to predict the entire computational domain. And in addition, the CNN prediction applies multiple times to predict the time evolution. And the first input is here is created by the LBM simulation, that the conventional simulation method. And thereafter, the CNN, the result are used as the input for the next prediction. And here is the prediction result for the time-dependent flow. So we show the result, the prediction, the velocity field, and the top side. The top side is the figure the LBM ground truth, and the bottom figure the CNN prediction. So note that this is the black is means that is the only data. Just there is only data in the LBM ground truth. That is the first the initial input, and here is the and after that this result is just CNN the prediction. Okay. And here is another example. Okay. So as shown in this the movie, the models will predict the LBM ground truth. Okay. So the point is that originally the training is done using the 64 times 64 the data, but this figure is the 1,000 times the 1,000 data. So that's too large. So here is the summary of my talk. So we have developed the deep learning, the fast prediction method for the steady and unsteady flow. The steady flow case is the prediction simulation result on large domain using a CNN with the boundary exchange, and that proposed method has no limitation for the device capacity, and the time in the case of the time dependent flow, the prediction simulation flow using a 3D CNN. So the applying the CNN multiple times, that's so long time the prediction can be made, and the applied the patches, so the prediction can be made for the region beyond the size of the training data. So thank you for your attention.
Okay, so thank you very much.
So thank you.
Okay, so let's move to the final talk of the first part of this lecture. It's by our keynote speaker, Professor Richard Ludwig from Georgia Institute of Technology. So it's my great pleasure to invite him to this workshop. And actually, so I invited him many times to Japan, but so this time is very special because after COVID-19. And Rich and I have been a long-time friend. So since he was a PhD student of the UC Berkeley, and so now he's a professor at the Department of Computer Science and Engineering of the Georgia Institute of Technology. So title of his talk is Data Movement Accelerators, DMX, and it's a very exciting topic.
Yes.
Okay, so please welcome our invited speakers.
Thank you. Thank you very much, Kengo, for the invitation. And thanks to all of you for allowing me to attend this workshop. I've already learned a lot from the meetings so far, and I'm looking forward to the continued discussions during the breaks and tomorrow. So this talk will be a little bit different than the ones we've seen so far. So since part of the BDEC project overall is about hardware and systems, I thought I'd give a talk about a component of emerging systems that I think is worth paying attention to, and that might be part of the future fabric of high-performance computers. So in the same way that when GPUs were introduced, they caused a kind of disruption in the way we thought about applications and our approach to parallelism and this design of systems, I think data movement accelerators have the potential to be one sort of a similar example of something that is like GPUs. The name data movement accelerator sort of is designed to contrast with the idea of a compute accelerator. So I think of a GPU as something that makes computation faster. A data movement accelerator is something that makes communication faster or better or easier to overlap or hide. So the cartoon that you see here, this, a typical, if we think of a typical cluster supercomputer system, there are nodes, there are host processors, and there are network interface cards that connect all of the nodes in the system. The idea of a data movement accelerator in the context of a network means that instead of just a network interface controller that's responsible for moving bytes in and out of the node, we'll actually put processors and memory and maybe even a whole memory hierarchy and basically a mini computer in the NIC itself. So now this is a new computational device that will be available on your systems. And the idea of a smart NIC, so a network interface controller with computation attached to it, is a very old idea. So when I was a graduate student, the network of the day was MiraNet, and MiraNet had processing. The reason why this old idea is interesting again is because smart NICs are being being reintroduced and produced possibly in very high volumes. So in the same way that when GPUs were produced in high volumes and they became cheap components that we could add into our supercomputing systems, the same potential exists for something like a smart NIC as well. And the target applications are not HPC. So the target applications are things like this. So, streaming video or other web cloud applications. Companies like NVIDIA have acquired hardware companies and are investing money in smart NICs because these are their customers, basically cloud systems. Now, when we think about smart NICs, there are actually a variety of things that are available today. So, the idea of putting a processor, what does a processor mean? So it could be everything from a special, fixed function ASIC. It could be a GPU, it could be an FPGA, it could be a multi-core CPU. For the things that I'll be talking about today, we've been experimenting with a platform that is available from NVIDIA that features multi-core CPUs as the processing element. But the concepts that I'll try to highlight at a very high level, I think apply regardless of what sort of processing substrate you imagine for your smart NIC. Okay, there's another term. So NVIDIA, in referring to its smart NIC with a general purpose multi-core CPUs on it, it refers to that thing as a data processing unit or a DPU. So that's what they call it, but it's just their sort of company specific jargon. So I'll use the terms smart NIC and DPU and data movement accelerator or DMX kind of interchangeably through the talk. But they are there are some subtle differences we can talk about offline. Okay. So smart NICs. So the reason they are being produced in mass volume by companies like NVIDIA is because they're going to sell them to cloud providers for use in data centers. So are they relevant to HPC? And I think the answer is yes. And it's for a very well understood reason in this audience, which is communication is an inevitable bottleneck. So what do I mean by this? So it's inevitable bottleneck in the sense that, our dominant paradigm for doing the dominant paradigm in computer science is if I give you an algorithm that has a high complexity, your goal is always to drive complexity down. And let's suppose, some hypothetical computation that scales like n squared, the first thing you ask, in CS 101 is there a linear time version of this algorithm? And the reason we are driving down computational complexity is to save energy. So the fewer operations you do, the less energy is required, the less storage may be required for, say, intermediate results and so on. Okay, so this is the dominant paradigm. So what does it mean if you are successful in this sense? Well, if you achieve something that scales like linear time, the percentage of those operations that are spent on communication necessarily increases compared to, say, the maybe asymptotically suboptimal algorithm. So if the driving paradigm is we want to make things as efficient as possible from a complexity point of view, then the percentage of time in those resulting algorithms has to increase. Okay, so that's one principle. The second principle is something that I refer to as the iron law of parallel and distributed computation. So this is something that you will understand very well, but I'm going to try to explain it in a slightly different way, and I will use this different description later. So if I imagine a hypothetical cluster type system, and I'm thinking about the cost of executing code on this system. So this system, there are really kind of two costs related to communication. One is moving data within the node through the memory hierarchy. So from main memory to the processor through maybe one or more levels of cache, as illustrated here. And then the other cost, of course, is moving data throughout the network. So how long does it take to run a computation? Well, there's the time to do operations, the time to move memory, the time to move data in the network. And whichever one of in the best case scenario, when I can perfectly overlap these costs, the best execution time will be the largest of these three components. Okay, and if I just refactor this a little bit, what I'm labeling tmem over TOP, that's what I'll call a memory penalty, and tnet over TOP is a network penalty. So think of TOP as the ideal time, but because we have to communicate, we will pay penalties either for memory movement or for network movement. Okay, so if you tell me that the processor runs at a certain speed, and you tell me that you can move data through the memory hierarchy at a certain rate, and you tell me you can move bits through the network also at a certain rate, then and you tell me kind of in your memory hierarchy how much fast memory, so think of this as like cache memory, how much fast memory is available, some capacity, which I'm labeling Z. Then the iron law says that the memory penalty and the network penalty have to scale like what's shown here. And just very briefly, the factors you see on the left, these are the usual processor to communication kind of operations per byte ratios. So what I'm calling R0 or B0, that's the ratio of operations per byte that the processor can do with respect to memory, and then R0 over BNet is the same concept, but relative to network communication. So you want these factors to be, according to the iron law, to keep the memory penalty and network penalty low, you want these to be small. So smaller is better. And that implies that the kind of processor you want as a building block should be smaller. Now, there's a limit to how small, and that has to do with these factors on the right. So these functions, these are kind of hypothetical functions. Think of them as increasing functions of the parameters. So g of z is some increasing function of, say, cache size. H1 of p is an increasing function of the number of nodes in the system. And then H2 of n is an increasing function of a problem size. So what do these say? So so there's one factor here that says, well, the network penalty will grow if you have a larger network. So if I put more nodes in the system, there's some parallel communication overhead, and this has to increase. So this actually suggests that what you want are bigger processors, because so bigger, if each processor is bigger, and I'm imagining two systems that have the same peak, the one with the bigger processor will have a smaller P. And so the network penalty you can sort of keep as low as possible. So essentially there's a trade-off. There's a trade-off between kind of memory and network communication, and this is a fundamental principle. So the two pieces again are communication. Communication is inevitable, and of the two types of communication, they have to trade off in some way. And we should think about system design and algorithm design as essentially techniques to manage these trade-offs. Okay, and then this other factor that's related to n, if I think of n divided by p as kind of the per node problem size, then the fact that there's something similar to n over p in this iron law and the network penalty essentially says, well, one way to reduce the network penalty is to use weak scaling instead of strong scaling. So again, these are all kind of similar principles, but I've kind of wrapped them in a slightly different way. Okay. If you ask, well, how do the principles work? How do we visualize or kind of imagine the principles in action? If I imagine I'm doing a very large matrix multiplication on two supercomputer systems with the same peak performance, one with big processors, that's the left, and one with small processors, that's the right. And I look at the scaling of, well, how does compute time, network time, and memory time scale? For something like matrix multiplication, you can see, well, compute and network time, those are the two largest factors. And they are scaling at different rates. So as you scale, if you're in the strong scaling regime, then as you scale, eventually these things have to cross over. So there's some kind of trade. So this is the trade-off that the iron law says exists. This is how it manifests. If I look at this trade-off between big sockets versus small sockets, an interesting thing you'll notice is the small socket system remains compute bound. So that blue line on the right, that is higher than the other lines. So this thing is compute bound, at least up to whatever scale is shown there. And as a result, as network time begins to dominate in the system with big processors, then network time starts to increase. And in fact, this is a log scale on the y-axis. So there's something for this, whatever this model is predicting, there's something like a factor of 2.5x difference in performance. So this is about 2.5x slower, this one with big sockets. So if you think about the systems we're building today, primarily the largest supercomputers are the things on the left. And they are just accelerating. What they're accelerating is the rate at which network communication becomes a bottleneck. So that's one point here. And I got a nice tour of the Wisteria system today. So I did the same. I just plugged in the similar numbers for two hypothetical Wisteria-like systems, one based on A100s and A64 FXs. And the principles are the same. Okay, so that now matrix multiply is something that is nominally compute bound, at least until you reach a certain scale. So what about something that is intrinsically communication bound, like a large multidimensional FFT? If you look, so here, the communication costs, the sort of green and red lines, those are the bottlenecks. And you can see that because they scale at different rates, they trade off. So this is an example of communication trade-off between the two types of communication. And again, this is an example where the small socket system actually gives you better scaling kind of in the long run. Okay, so the conclusion so far is communication is inevitable. And the reason we care about system components and these sort of heterogeneous designs is we should think about the components as helping us manage these trade-offs that affect scalability. Okay, so that now brings us to kind of smart NICs and DPUs and these data movement accelerators. So again, for this cartoon system, what are the things that people are talking about using DPUs and DMXs for? So there are many ideas. The commercial one is accelerating network applications that run in data centers. So these are things that classify packets or help adjust the shape of traffic or help implement multicasting. So those are things that are not really of interest in the HPC world. Things that are related to improving network and storage performance, or if you imagine systems that are coupled to high performance sensors, this is now a region where I think for future applications, DPUs will be interesting. And then there are lots of other interesting ideas related to kind of runtime management. So helping to implement fault tolerance schemes, data management, and do load balancing. Those are things that I think are of interest in HPC. And the thing that in my lab, a couple of my students have been thinking about is, well, what about HPC algorithms? So I'm just going to give you a very brief summary of some of the things that they're thinking about there. And they've been looking at, I think just in the interest of time, I'm not going to talk about these in too much detail. But two kind of toy applications that we've started doing experiments with on real hardware are one comes from molecular dynamics. It's a proxy app called MiniMD, and the other one is called MiniEM for electromagnetism, and it's related to computational electromagnetics. Okay, so so when you think about a smart NIC device, two ways in which you could imagine using them are what some people refer to as off-path versus on-path computation. So off-path, well, on-path is the simplest one to understand. So as a message comes in, you have a processor on the NIC. This processor does something to that incoming message before passing it on to the host to do other work. So that's a very interesting thing. That's something that actually we're starting to look at. And I think many of the ideas that we've heard about today that are related to changing precision, doing mixed precision, maybe helping to manage communication related to the ghost regions in the context of sort of domain decomposition methods, doing compression of messages on the fly. These are all interesting kind of on-path activities. Now, the hardware that was available initially was not good at on-path. So basically the processors on these NICs, they're very weak compared to the host processors. And so there's not enough computational power there to do anything interesting. So a different way we could think about it is the off-path method. And in the off-path concept is, well, let's just think of this as kind of a big little processing system. So it's a heterogeneous system similar to kind of like CPU, GPU systems where there are relatively weaker and stronger processors. And we try to do some kind of task asynchronous offload to the smart NIC. So that's the one that we started with because it was hard to make the on-path faster. Now there is new hardware. There's a new generation of hardware where on-path might be feasible again. So we're starting to explore that. Okay, in the molecular dynamics example, so just to give you a sense of when I say sort of strong and weak processors, on a particular hardware platform that we've been using, the host CPU in terms of its rough characteristics, peak FP64 performance is like 650 gigaflops, and memory bandwidth is on the order of say 76 gigabytes per second. This NIC processor is much weaker. So it's almost like a factor of 8 slower in peak and a factor of 3 slower in memory bandwidth. So absolute performance is weaker. but there'll be an interesting kind of twist and surprise later that maybe you can anticipate already. In the, let's see, I guess maybe rather than explaining the exact technique, let me say that the original mini EM application, if I imagine how it executes as a timeline, there are a series of tasks that have to be performed, and there are sequential dependencies between these tasks. So the FC task depends on the C task, and that in turn, depends on a UV task that happens earlier. And the only way to create work, and the tasks themselves can be parallelized, but parallelism across tasks does not exist. So the only way to create it is to break the algorithm. And that's a non-trivial change. It's not something a compiler can do automatically. It's something that you have to use algorithm knowledge to do. So it turns out it is possible to break that dependence and create a small task that you could then offload onto the device. So this technique was possible, but it required kind of rejiggering the algorithm. And so I think of this analogous to GPUs. In order to really use GPUs well, very often you have to rethink the algorithms. Okay, so in the process of doing this, my student Sarah, who worked on this, was able to eventually, through appropriate kind of offloading, speed up mini EM, not by a factor that will sound large, something like a 20% speed up. But I think to take this speed up in context, adding the SmartNIC to the system only increased the power of a node by about 6%. So for only a 6% input, you got a 20% speed up through this extra asynchrony and through what turns out to be a more power efficient processor that's available on the SmartNIC. The other kind of interesting observation that she made, so I said that, well, the SmartNIC processor is much slower, but if you controlled for peak, so if I imagine putting 8 SmartNICs together as a little mini cluster, you could roughly match on peak and you would get way more bandwidth. So for things that are communication limited, if they can be distributed and offloaded to many SmartNICs, then you can get much more efficient performance from this kind of system. And the reason I point this out is I think this is an interesting way that's not really using SmartNICs in the way they are intended, but if you assume these are commercially available, I think one important question for heterogeneous computer platforms is, well, how many of each component do you want to buy? So I think for the Wisteria system that many of you have been using, for example, maybe it's like in terms of peak performance, it's roughly a factor of 2 to 1 or 3 to 1 between kind of the large general purpose CPU part and the one that has GPUs on it. So this question of how to balance the components in heterogeneous system is always an interesting system design question. And if communication is inevitable and the building blocks for SmartNICs are actually kind of more balanced, so in the sense that the flop per byte ratio for these guys is better than the one for the heavyweight processors, then maybe there are designs for systems where actually you think of the SmartNICs as most of the processing, and you offload kind of to a host. Okay, so let's see. The other application, this EM one, is related to algebraic multigrid. This is still work that's in progress, but kind of a preliminary implementation is giving similar results to what we saw for mini-MD. Other things we have looked at include multidimensional FFTs and sparse direct solvers, distributed direct solvers, where similar findings related to what I said for mini-MD apply. So even in systems where we just put make one SmartNIC available on the node, we can get speed ups that are larger than the power footprint that's required as input. So to conclude, the main message of this talk is just the reminder that communication is inevitable. So thinking about what are the things that we can do at the system level, and then based on the system level changes at the algorithm level through some kind of restructuring. How can we exploit devices whose target is communication itself? And so I think this will be an important future area. There are lots of open questions related to this. One thing that was very difficult in the work I described was programming, but I just thought I would mention in case that was a question that you had in mind, and is the thing that made GPU successful was having a programming environment that people could use. There's some interesting new work from the Barcelona Supercomputing Center where they've essentially implemented OpenMP target directives to be able to offload to SmartNICs. So that's a capability that is just now coming into play, and it was otherwise very difficult to do the experiments that I mentioned earlier without this capability. Okay, so I guess I'll end there, and we can move either to quick questions or the discussion. Thank you for your attention.
Okay, thank you very much. So, any questions for Rich's talk? Okay, thank you very much.
All right, thank you.
Okay, so let's start the second part. And the first speaker is Professor Takeshi Ogita from Waseda University. So he will talk about the accuracy. So please start your presentation.
Thank you very much for my introduction. So today I'd like to talk about this topic. So I'm from Waseda University, and this is a joint work with Professor Nakajima at the University of Tokyo. So the goal of this study is to develop verified solution of linear systems discretized from a three-dimensional Poisson equation that is frequently used for benchmarking in high-performance computing. Concretely, we treat this type of heat equation, and the lambda is a thermal conductivity, and so this right figure shows the cross section of this cube. So at the middle point, the lambda 2 is considered as a thermal insulation. So if lambda 2 is decreasing, then condition number of this this problem increases. Okay, so that is what we focus on. So we first discretize this type of a PDE by finite difference method or finite element method. Then discretization error and rounding error occur. But we obtain linear system. Then we apply some iterative solver such as a conjugate gradient or GMLess and so forth. Then we obtain approximate solution. So in this talk, we consider only this part. So some rounding errors occurs by solving linear system. Okay. So now that is a condition. So we apply, we use a 7-point FDM mesh and discretize by finite volume method. Then matrices have M property. This means the inverse of A is non-negative. And we can apply fast verification methods for linear systems with M matrices. So here is verification algorithm. So the first step, we solve a discretized linear system, AX equal B. Then we obtain a computed solution, X hat. Next, we solve a linear system, AY equal E. So this E is where all elements of E are all ones. So right-hand side of this is replaced by E. Then we obtain a computed solution y hat. And next, we verify M property of this coefficient matrix A using this computed solution y hat. So, and we check this positivity of y hat and A times y hat. Okay, so if this is satisfied, then we can verify M property of A. And next, we compute error bound of computed solution x hat using this inequality. And we need to check the norm of this residual E minus A y hat is less than 1. So if this is satisfied, we can use this inequality. The important point is that this right-hand side can be computed by obtained computed solution and residual. So all the quantities can be computed. Now I'd like to show some numerical results. We use this computer and we use a ICCG solver, and the stopping criteria for ICCG is used as follows. So for AX equal B, we use this stopping criterion, and AY equal E, we use this stopping criterion. So please note that for this linear system AY equal E, we only need this. So this is relatively larger than this stopping criteria because we only need this norm is less than 1. Okay, and we use double precision arithmetic and with open MP. So here is a result. So we show per bounds of maximum relative error and the relative residual norm. So this is a result for relative error. So this is around 10 to the power of minus 8. So this means computed result has a correct decimal digits is 8. And the residual is less than around 10 to the power of minus 11. And this is a computing time for so to compute approximate solution. And this is so computing time is 3.75, but for verification, we only need 1.6 seconds. Okay, and so these are the number of iterations for ICCG solver. Okay, and this one is so horizontal axis shows the condition number of the problem, and so lower is better. Okay, and this solid line shows the error bound of a computed solution, and this dot lines shows the residual norm. So from this one, it can be seen that it is difficult to estimate the error of a computed solution only from a residual norm because there are gaps between residual norm and error bound. Okay. So, so now we like to improve this phenomena. So to reduce the overestimation, we replace this estimation by this formula. Okay. So the correction time, this z hat is obtained by solving a new linear system AZ equal R. So right-hand side is replaced by R. So that is a residual of this linear system AX equal B. So using this formula, we can improve the estimation of error bound. Okay, so here is a verification algorithm. So we from steps 1 to 3, the same as before. But next step, we compute this residual b minus ax hat. This should be computed accurately. Okay. And the next step, we solve a linear system A z equal r hat, and we apply this error bound. And we show numerical results. And we need to solve a linear system A z equal r. And the stopping criteria is this relative error is less than 10 to the minus 9. Okay. So here is a result. So so similar to the previous result, the horizontal axis shows the condition number, and lower is better. So now this is the previous error bound of a computed solution, and the red line shows the new error bound. So this is almost similar to the residual norm, so that the computed error bounds are significantly improved. And so these tables show computing time. For this size of a problem and the condition number, this is a so computing time is that one, and verification computing time of verification is about 4.5. So this is comparable to the computing time for obtaining approximate solution, and for larger condition number problem, the similar result is obtained. And for larger problems, similar results are also obtained. Okay. So, okay, so we, I'd like to summarize this study. So we develop efficient algorithm for sparse linear systems with M matrices. So, and there are future works. So first is to accelerate a verification process. So more precisely, we like to apply a mixed precision approach, and we also optimize the algorithm for double right-hand side, because we solve 3 linear systems, and at least this AX equal B and AY equal E can be computed in parallel. So this AZ equal R hat, we need the result of the AX equal B, so we cannot parallelize. Okay, and second is to consider the discretization error from PDE, original PDE. And third one is to develop efficient verification algorithms for other matrix classes. So for example, positive definite matrices, because this approach can only be applied for M matrices and H matrices. So if we can develop some verification algorithm for positive definite matrices, there are much applications. So, これ時間大丈夫かな? Okay, so that's all. So thank you very much.
Thank you very much. Yeah, we still have a couple of minutes. And any questions from the audience? We still have 2 or 3 minutes. So if you want to add something, you can do that. Professor Ogita.
あ、僕ですか。
まだ時間あるから、もうちょっと。
はい、なるほど。13分ぐらい。なるほど。そうですね。じゃあ、このミックスドプレシジョンアプローチについてなんですけれども、はい。 So, for example, the idea for mixed precision approach is to apply. So, for example, single precision arithmetic for solving a y equal e, because we only need this stopping criteria. So this can be, I think this can be achieved by using a single precision arithmetic. So this, I think the double precision arithmetic is necessary to achieve this one, but for solving this one, we don't need double precision arithmetic so that we can accelerate the ICCG solver. Okay.
Okay, thank you very much. So, any further questions or comments? Okay, if not, so it's time. So, thank you very much again.
Thank you very much.
Okay, so let's move to the next talk. It's by Masatoshi Kawai from Nagoya University. So, Kawai-san, are you ready?
Yes.
Okay. So next one is also related to mixed precision. And so, yeah, please start if you are ready.
Yes, thank you very much for introducing. So today I'd like to talk about these titles. And this is the brief indexes of today's talk. The initially I will talk about the objectives. So in this study, so I will consider applying the low and adaptive precision to the ICCG method. And as well known, so the low and adaptive precision is widely researched in many fields. But there's few researches for applying the low and adaptive precision to the practical simulations. But if you use the low precision to do the these simulations, so we can improve. We can reduce the computation times. And recently, so the FP21, so this is a kind of adaptive precision, is evaluated on the simulations on the GPUs. So in this study, so we evaluate the effectiveness of the low and adaptive precision with the iterative method. Method is in the ICCG method on the CPUs. So the ICCG is one of the most famous and iterative method, which require the high accuracy of the computations. But the performance of the ICCG method is determined by the memory bandwidth. So if the low and precision is useful, that we can reduce the computation time of the ICCG method. The next slide shows the data format which we use for these studies. And FP16, 32, and 64 is standardized, and it will be 754. But FP21 and FP42 is adaptive precision, so we use for these studies. But so we use FP22 and FP42, these adaptive precision, so we need data casting from the where we compute them. It is because this data format is not supported on the normal FPUs. On the next slide, show the expressive abilities of the data format. So it is easy to guess why the data format have a higher expressive abilities. And then, so this part shows the significant number of decimal digits of the decimal numbers. And this shows the exponent part, so the maximum exponent in decimal part. So the FP21 is the exponent part of the FP21 is the same as the FP32, but the significant part is lower abilities compared with the FP32, but a bit slightly higher than FP16. Same as the FP21, so FP42 has the same exponent part with the FP64 and the higher significant part compared with the FP32. So to use these adaptive precisions, as I mentioned above, so we need type castings when we compute these data types. So this code shows the absolute code. This shows the pseudocode of the data casting in the Fortran. So in this implementation, so we store 3 FP21 data to the 2 32-bit integers data format. The typecasting is very simple. So initially, so we cast the data type from float or double to the arbitrary integer type, and after that, so we omit the unused part and stored each data to the integer 32-bit integer data types. So in the original FP21 research, so they are using 64 integer data types to store the FP21. But the number of computations per one simulation is capped by the wide data format. It means if we use a 164-bit integer data type, so the simultaneous instruction per computation is capped to 8 data, but by using the, so this is our optimization, so by using a 32-bit integer type, so we can compute the 16 data per our simultaneous interaction. So this is our optimizations for the adaptive precisions. So this is a straight code for the FP21, but the FP42 is similar with a similar code. And so we use we get some effective by using the raw or the adaptive precision. So we have to use a fully use the memory bandwidth of the each systems. And then so we try to we use the acceleration sigma data format for implement the ICCG method. So the series is the most commonly data format for the sparse linear sparse matrix for the sparse matrix. But in this approach, so it is very difficult to use the simultaneous instructions, and it also difficult to fully use the memory bandwidth. To compare with that, so EA is used for the vector machine types. So by using this, if you use the AI type, so simultaneous optimization is simultaneous interaction is computed in this order, but the problem with this data format is there are many zero paddings. So compared with these data types, so celsius sequence is very good. It should have a good point for simulations and less zero paddings. So if we use the celsius sigma, so we separate the target matrix to some blocks. Now after that, so we sort each lines with the number of columns like this, and after that, so we separate these blocks with a chunk size. So chunk size is has a strong effect on the simulations. And each simulated computation is in this red arrows orders. So we use this celsius sigma format for the ICCG method. And the next, from here, so I'd like to show the result of the numerical evaluations. And so for the numerical evaluation, so we use the 3 systems. But I'm sorry, so that these 2 systems already retired, but I like to show these systems. The difference is the CPU. So the first system has a Xeon files, and the next one has a Xeon CPUs, and the last one has a A64 FX CPUs. The target application is same as previous Professor Ogita's talk. So I applied with a P3D application. So it is this heat condition problem, and this time with a findable method. And in the condition of my research, so degree of freedom is more than 16 million degree of freedoms, and the sound content difficulty is from 1 to 10 power 10. So the ICC, in the ICC method, so we use the cyclic match coloring and the reserve Fibonacci approach. And the number of color is 10 colors. If the relative reserve norm is reached to the 10 power minus 8, so we stop the iterations. As I mentioned, also search format is mainly search sigma, but for the brief comparison, so we also implement the SHA-RS and the ELLs. And also in the numerical evaluation, so with some combination of each data format for FP64, 42, 32, and 60, 21 and 16. And these denote as a data format of the matrix and vectors. For example, the FP42 and FP60, meaning the matrix is stored with the FP42 and the vector is stored with the FP64. And the blue part is only evaluated on the Forest Box and Oakbridge CX, and the green part is only evaluated on the Wisteria Odyssey. And the black part is also evaluated on all systems. And so also the FP60 vector is not included. It is because the computation is not converged. Okay, so before the detail of the numerical evaluation, so I will show the target application is using the fully using the memory bandwidth. So by using Celsius sigma, so the performance is very close to the memory bandwidth. The computational time of the Celsius sigma on the Wisteria Odyssey is here. So on the actual measuring, so the memory bandwidth is close to 80 gigabytes per sec. So the stream trial, the result of stream trial benchmark is about 840 gigabytes per sec. It's very close to this. So it meaning this program is fully use memory bandwidth. And compared with any other system, so the computation time is 1.9 and 3.3 times faster. Slower. But the memory bandwidth is also slower than the 3.0 and the 1.7 times. It is this number is very close to the stream benchmark. So it meaning that in any other system, it meaning we say Oakbridge CX and Oak Forest Spark. So the actual memory bandwidth is very close to the stream trial result. And the next slide, I will show the overhead of the typecasting from the adaptive precision to the standard precisions. So, for example, the FP21, FP32 meaning normal computations, and this dummy code meaning comment out the data casting, but we add another instructions for keep the same load memory rows. So it means that this difference is the overhead of the typecasting. On these results, the overhead of the typecasting is very small, so it is up to the 1.7. So this we determined that this implementation is acceptable. And the next slide shows the result, evaluation result on the each systems. And in this slide, so the low and adaptive precision only apply to the preconditional part. And on this graph shows the number of iterations on each system, and the y-axis shows the different thermal conductivities. On the good conditions around here are low precision. All precision, number of iterations on all precision is similar. But in the ill conditions, so the number of iteration is changed like this and any other systems. And the next slide shows the computational times of each systems. So as I mentioned, also the number of iterations around in the good condition is same. As a result, so we can get performance improvement by using a low or the adaptive precisions. For example, the FP32, FP16 and FP32 was the faster, 70.3% faster compared to the FP64 on the Wisteria Odyssey. And the FP2132 is 18.4%, 18.6% faster on the good conditions. Okay, from here is just apply to the preconditional part. And the next slide shows the result with applying the low and adaptive precision to whole ICCG method. So if we apply the low and adaptive precision to the whole ICCG method, so we have to consider the errors on the each data format. This figure shows the relative errors of this red point. So if we use the FP21 matrix data type, so data format, so in the best conditions, so the relative error is not so large, but immediately so the relative errors get worse. So it means that FP20 is very limited to use. Compared with this FP21, so we can't find any difference between difference of the FP22 compared with the FP6. So this is a very good result on the FP42, FP6 result. Okay, so the next slide shows the computational time of the each data format. So by using the low and other precision, so we can get performance improvement as same as the previous result. For example, for FP42 and FP64 is more than 10% faster than the FP64 or FP4, and it is constant on any conditions. And this is limited to the good conditions, but FP21 and FP32 is close to 40%. It meaning very close. It is close to the half computational time than the FP64 and FP64. So this is very good. This improvement is very good, but it is limited to the good conditions around here. So in other words, so the FP42 and FP64 is a reason acceptable on these applications. Okay, this is the summarize of this talk. So this is the brief summarize. And the future, so I would like to consider an auto-tuning approach to the dynamic select to the best data format. And I would like to evaluate more mixture predictions, for example, the FP21, 32 IC preconditional, and the 4264 CG part, and so on. Now I would like to evaluate, implement adding the verification part in the talk of the previous Professor Ogita's talk, and I would like to evaluate about this. So thank you very much, and thank you attention.
Thank you very much. So any questions or comments from audience? Okay, so now it's time, so let's move to the next one. So thank you very much.
Thank you very much.
So next talk is Yashiro-san. So he's also online. So he's from the National Institute for Environmental Studies. So Yashiro-san, could you share your screen? Oh, okay. Thank you very much. Okay, so he will talk about the coupler and some applications to the climate area. Okay, so please start if you are ready.
Okay, thank you. My name is Hisashi Yashiro from the National Institute for Environmental Studies. So I will talk about the climate studies and the coupling library, H3 Open Utility MP. So we have some directions about the demands on the HPC resource for weather and climate research. One is the resolution. In the world, now there are some operational centers considering about the kilometer scale weather prediction, the climate prediction, for more accurate the weather forecast and climate predictions. And duration is also important. The climate simulation is more than 100 years. So the 100 years means that the 10 million time steps required. And for ensemble, we are increasing the ensemble members for the more robust statistical results about the simulations with the uncertainty. And the climate model and weather simulation model have a lot of the components. So that we want to use more sophisticated model components so that the model complexity is increasing and increasing. So almost all directions, we need more computational power. So the one example is the resolution. Actually, I'm the climate researcher, and some people ask me about why you need so high resolution simulations, and why do you need so large and huge computational resources. The reason is coming from the atmospheric phenomena. When the grid spacing is the order of the 100 kilometers, we have to parameterize the clouds and the convection processes. So that is the source of the large uncertainty. So that we have to we want to use more high resolution simulations. However, high resolution simulation takes large computational costs. For example, if we increase the resolution 10 times, the problem size is increasing to 1,000 times. This is an example of the simulated precipitation Diana cycle of the Amazon region. In this region, observation shows late afternoon peak of the precipitation. However, if we use the 100 kilometer mesh resolution simulation, the precipitation peak occurs in the early afternoon. So that is too early. However, when we increase the resolution, if we use the 10 kilometer mesh resolution mesh size, the precipitation peak shows midnight. That is too late. And when we use a super high resolution, that means the 1 kilometer resolution, such simulations reproduce the precipitation peak very well. So then we have to we want to use more large computational resource, but we are facing some difficulties. The trend of the HPCs, the changing, and the weather and climate models are huge, and it's very hard to port. And the memory throughput mainly determines our simulation speeds, but its memory performance will not improve faster as we expected. And our model has no large hotspots of computation, so we have to optimize everywhere in the application. In such situations, from this year, the ACM Golden Bell Prize for Climate starts. This prize encourages collaboration and further efforts between the climate science and the computational science. In this month, the first winner was determined. The first winner was a very big team in the US. They have rewritten the atmospheric model, whole of atmospheric model with C++ template. That was a very hard work and the big team work. And such the huge changing is required in our research region. So today I will introduce about the two practical cases for using our coupling library to solve the computation the problems related to the HPC. We developed the coupling library H3 Open Util MP, and today I will introduce about the reduction of the computational cost of high resolution weather data simulation. And the next one is the reduction of the computational through the making of data-driven surrogated models. I will introduce about the ensemble data simulation. The ensemble data simulation is merge the information from between the observation and the simulations. In this data simulation technique, we use the ensemble simulation. So total computation cost is come from the one-member simulation and the number of ensemble members. When we increase the ensemble members, the computational cost increases. And on the other hand, when we use more high-resolution simulations, the computational cost also increases. However, we want to make such huge large-scale computations because the low-resolution simulation has a lot of uncertainties, and that the low-resolution simulation does not reproduce the local size phenomena, such as the heavy rain and the detail of the typhoon. However, the high-resolution ensemble simulation is very costly. When we make this ensemble data simulation, we have to consume a lot of the computational resources. So we designed the online coupling between the low-resolution ensemble data simulation and the filtered NASI. In the left side, that is the ensemble data simulation system that is consists of observation data and the ensemble simulations and the ensemble Kalman filtering system. In this system, we use the low-resolution atmospheric simulations. That cost is very cheap. However, the result is very cost in this spatial aspects. So we coupled this data simulation system under the high-resolution one-member simulations. The data simulation result and the high-resolution prediction result is compared in the low-resolution world by using the remapping feature of the coupling library. And the difference is applied as a nudging tendency to the high-resolution simulation. In this system, we also can obtain the realistic atmospheric state. In that state, for large-scale component is come from the nudged information from the low-resolution data simulation, and for the small-scale phenomena is the explicitly simulated in the high-resolution simulations. And to achieve this system, we develop the expands the feature of our coupling library, and so our H3 OpenUtil MP is now enabled the ensemble coupling. In the coupling layer, data exchange is data is exchanged between the different models with grid mapping, and the M and N data transfer is enabled. Then the ensemble layer, the data exchange is managed by our coupling library between the same models. in this layer, gather and scatter on the same area of different ensemble is done, and the average calculation of ensemble data is also obtained. So this is now we are executing this high resolution, low resolution data simulation coupling system, and this is the estimation of the computational cost. The upper part is a high resolution ensemble data assimilation case. In this case, we use a 14-kilometer mesh and 64 members, 64 ensemble members with the 640 MPI processes per member. Each 8 members is executed simultaneously. So the 8 times is required to all of the members execution. The 0.5 simulation per day per wall clock hour SDPH is obtained with the 1028 node of the Wisteria Odyssey. The lower part is the new system. In this system, the ensemble data simulation part is executed with the 224 kilometer mesh, and in this part, the half of the 640 node is consumed, and the filtered nudging part is consumed at the same number of nodes with executing the 14-kilometer mesh one member simulation. In the total, the two simulations are almost overlapped. So the total execution time is determined by the filtered nudging part. The almost 20 times faster than the high resolution ensemble data simulation. So next is the reduction of the computation through the making of the data-driven surrogated models. So now AI weather model is the very hot topics, and each surrogate simulation results it's almost equal to the full model. But we are climate and weather scientists, so we will not throw away the physics model from now in the future, and we want to apply new techniques step by step in the huge code-based software. So we need the component level surrogation by AI techniques to make a booster. So for this purpose, we developed the coupling library, and this coupling library connects the Fortran legacy application and the Python written the machine learning library, and by using the ASE OpenSys WaitIO socket together, we can use the different heterogeneous supercomputers such as Wisteria BDEC. So this presentation is done by the Sumimoto-san. So this is the preliminary result of the crowd microphysics scheme, and we get the preliminary result of the machine learning output. So this is a summary. The weather climate model still needs a huge amount of the computational resources. So that we are solving some issues by using coupling library. Thank you.
Okay, thank you very much. So any questions or comments? Okay, so the time is a little bit ahead. No, delayed. So let's move to the next topic. So thank you very much again.
Thank you.
Okay, so next talk is by Shinji Sumimoto from University of Tokyo. So his talk is really the previous one, and was a WaitIO library was a heterogeneous environment. Please start. We are ready.
Thank you very much for introduction. Okay. So I'm talking about some HC get WaitIO. So, question, thing Nakajima will talk about some issue of the project. My talk is about some software and utilities for theoretical computing, such as visual. And as you maybe Professor Nakajima talking about some visual there are also two types of nodes. There are heterogeneous node, and one is the simulation node. Let's say it's an ARM CPU and a TOF-D interconnect. And the other one is the Aquarius. It's a Intel GPU and NVIDIA GPU and Ethereum GPU. And also, two CPU are connected by 2 terabyte WaitIO network and also some two type of shared files, high bandwidth shared files. So, what is the HC OpenSys WaitIO? It's a commercial library for heterogeneous coupling computing. So, Professor Nakajima talked about some of the things, some of the real-time aspect situation, and this is real-time simulation with data assimilation calculation result and real-time data. And also some of computation, there's just some machine learning data. Also, Yashiro-san talked about the previous talk. So we believe that the fusion of the multiple application is a key with simulation, data processing, and machine learning. That's because we are proceeding from heterogeneous coupling computing by WaitIO. Here's some real-time heterogeneous coupling computing using the real-time passive expansion. These are coming to the original data. Interactive function analysis. Real-time data. This thing with the WaitIO 6 socket to send the number. Let's say computation, a simulation node by using some using Seismic 3D open SFC PAF and use the data together. And just example is the simulation by Poisson, maybe previous presentation by Yashiro-san. So how do you think? It's very simple. This is a API for WaitIO. Each operation is defined by parameter. So several multiple parameters can be come together and some thing that is together. But very simple. WaitIO, I think, ICCG, and wait, that's all. It's basically some MPI computation, but also some of mysterious computation. So, but some WaitIO API very simple. Too simple is this not so good because some WaitIO doesn't have an MPI data type. So we developed the WaitIO MPI conversion library for them to convert the MPI program to WaitIO easily. It's an API and reduce gas and all kinds of such kind of thing. Together, now we're developing and it's implemented by request. So this is some of example of using my coupling application. This is a very toy application in coupling WaitIO.
Sorry. Sorry, hi there. And this is some very simple application. So it's the code 1, it's very coding some source calculation, and code 2 and code 3 is some providing some calculation in the YouTube by FEM. And this case, this code 1 is maybe it's a file on some S1 out and some S1 out is reading some code 2 by code 3. So how do you fix that? The basic process is the file based. It's maybe a photon program, is this open and read and close, and this is the output in the open for the write and write thing. So how does this thing? It's WaitIO. This is some of header file and allocation some and this is the initialization of the WaitIO. At the time, I will go to the send and receive instead of a file write. That's only. Just is some really easy to implement some of the peak 3D application conversion. This is the red things maybe adding a code to the original code. So using an MPI conversion library, this you can easy to put in a WaitIO underscore prefix. That's only for the functions and data types and some operations that you can see. It's very it make conversion machinery computer. So and also WaitIO is coupling some data H3 open UTMP, but this is presented by previous talk. It's a conversion varies in Odyssey and accuracy by in some of the computing. So how to run the sum of workload? There are total number of nodes. This such kind of maybe Poisson talk about such. This is a kind of different item. Each system is operated by a different job schedule, but all same as teach which job schedule. So, to couple with some the job can be progressed, we developed a WaitIO hostname server because some of for the batching system, hostname is defined but at the runtime. It's very difficult to tell. So we need some exchange of host information to the several couple of jobs. So that is because hostname is provided. And also a couple job execution service. This is some of a type of procedure. When the user job is submitted, the job is can change the hold, still hold. And the cost schedule, looking at some each job schedule, it's some of it's a resource available. When both required resources are available, the hold to the pushing the jobs to the side, execution running phase. So how to do that? So coupling job execution sequence. Just because if you want some of the coupling job, you use a specified some of resource unit, special resource unit, maybe a couple underscore, some couple underscore, or something like that. It is, and if such kind of couple job is specified, the sculpture works there. And do the simulation execution when resources are multiple systems are available. And also, if such kind of job is scalable, so the control cost scheduler prepare and some WaitIO socket execution environment because such kind of environment variable. So here is some of performance. WaitIO is a sum with a WaitIO socket based in the using communication by a socket, and also WaitIO on the file is using some shared files. And WaitIO hybrid is a combination of the WaitIO socket and WaitIO file. So here's a communication performance. Y-axis shows the number of message sites, and Y-axis shows the megabyte per second. And you can see that here is some of WaitIO socket. WaitIO socket is here, and the WaitIO file is kind of here. And combination of the here is some of WaitIO file by into some 6 nodes, and here the WaitIO hybrid. Because some of WaitIO hybrid is higher, because using a WaitIO hybrid, Lambda protocol is accelerated by a WaitIO socket. This WaitIO socket is not so good because CPU power limitation. So here's some of performance results in the H3 Open UTMP and H3 Open Sys WaitIO. And here's an example of Nikon AI and performance evaluation on the coupling computing. This is a total density in internal energy and density of power value. And a framework, a pipeport method, and 3-layered MLP. And here topic summary evaluation result, and just show the result. And here's the performance. Here is a NICAM, which is a homogeneous. It is a NICAM and ADA is on the Odyssey. And here is the NICAM in the Odyssey and ADA in the Aquarius. And you can see some socket and file and hybrid thing. And you can show some WaitIO hybrid is the best on the hybrid. Because of this is the Odyssey and Aquarius is the gateway, using gateway. That's the bottom. And here is summary of the WaitIO socket. And WaitIO socket is a high-performance system-wide combination for coupling multiple MPI applications among multiple heterogeneous systems, and no extra software needed. Works among the system with a project socket combination and shared files with the raster, like project file shared files. And also, most important thing, existing programming tuning environment, existing MPI and compiler can be used. That's a very important thing. Based on the existing tuned application, on top of the adding some WaitIO combination, you can do the coupling computing. For example, Fujitsu MPI and NTMPI and OpenMPI, it's a coupling combination with a different pressure. And whichever we are developing some WaitIO bugs for infinite band and low-key and slingshot. It's not working. It's around some almost in the visual case 1.3 microsecond one way, and we are 20 around 34 gigabyte per second bandwidth. It's almost same as the NPM. That's my end of talk. Thank you for listening.
Okay, thank you very much. So any questions or comments from the audience? Okay, thank you very much again.
Thank you very much.
Okay, so next speaker is Hayato Shiba from University of Hyogo, and he will talk about some graph neural network based molecular dynamic simulations.
So let me start. Thank you for the introduction. And as probably Nakajima Sensei mentioned, I had been at the Information Technology Center until March 2023 and moved to the current position in the last April. My workplace is now Kobe Information Science campus of University of Hyogo. And this is located next to Fugaku RCCS of Riken. And I am sorry for not being able to make it in person today. We had an internal meeting where we listened to 5-minute presentations of all 80 master students here, and I am temporarily quitting from this meeting. So as the title says, I will talk about the glassy deep learning of simulated glassy dynamics. So I apologize in advance that my talk will be strongly oriented in physics today, and due to the limitation of time, I cannot mention today, for example, computational aspects like speed of benchmarking, for example. So what are glasses? So glasses are formed by rapidly cooling a liquid. So this is a very mysterious thing, and they have random structure as if they are being liquid, but it doesn't crystallize. And just by rapidly cooling it, it frozen like a solid, keeping its disordered structure. So therefore, glasses are liquids with diverging dynamic timescale. In other words, if we, for example, observe, and this is the experiment data, and as a function of the inverse temperature, so going to the right, the temperature is lower, and then we observe a time scale of a diverging time scale like this by more than 10 orders of magnitude. So in physics and material science, the central question is why such drastic slowdown happens without the changes in the structure. And molecular dynamics simulation is an important tool for clarifying it, as we can get hints from the dynamics instead of the structure by doing a simulation. But unfortunately, we can simulate only up to 7 or 8 orders of magnitude time scale at the best by using this is the limitation of the simulation, current molecular dynamics simulation. So we are trying to do the best, but we are in short of the time scale. So we are doing the best, trying to do the best within this limitation. And one of the central problems in this field is to predict the dynamics from the structure. So, by looking at this structure, so this seems random. So there is no hint regarding, for example, where the particle rearrangement begins. So particle rearrangement is very slow, and but it should begin at some place. And what we know is it is not completely random. And if we are given one structure, reproducibly, we have the dynamics like this. So I am visualizing here. We are seeing the visualization of mobile and immobile regions. So mobile regions are reproducible. So the problem is whether we can predict such heterogeneity in the motion from the random structure with no hints, structural hint. Recently, machine learning has appeared as a strong tool for the search of such structure dynamics correspondence. So by using initial random structure as the input of machines or neural networks, and training them with the dynamics extracted from a bunch of trajectory data, then we can possibly have the access to the structural dynamics correspondence. And this stream of research has begun to spread, especially around 2015, as far as I recognize. And people have begun to use first support vector machines or other kinds of linear machine learning models. But further in 2020, DeepMind people, Google DeepMind people, had made an impactful proposal of using graph neural networks. So this has made a bit of a boom in the specific field. So here is what DeepMind team has proposed in 2020. So we have the initial structure of glasses. So this is just a cartoon, but the system is actually in 3 dimensions. And we try to represent the system by as a graph by regarding the node as a particles as a node, and connecting between the neighbor particles by edges of the graph. Then we process it on the neural network. Then make the output the particle motion of the node. So what we do is for certain number of structures, we do the molecular dynamics simulations, a lot of simulations for different structures. Then we make the dataset of the particle motion, and then let the GNN graph neural network run it. So what they realized with this graph neural network is high predictability of the particle motion. So I'm plotting the Poisson correlation coefficient, which represents how GNNs precisely predict the particle motion of each particle as a function of time. So so for a typical time scale of glassy relaxation, just note this is a simulated glass, so the time scale is limited. So it corresponds to, for example, the 10 to 6 time step of MD simulation. And here they have the Poisson coefficient of 0.6, which is regarded as a kind of state of jazz at that moment. And our neural network has been proposed in 2023, and this is designed to resolve this some problem, and just by adding the target quantity on the edges of the graph. So we let's just let the graph neural network to run in addition to the particle motion, the relative motion between particle pairs, which are located nearest neighbor. So this network, we named this network as bond targeting network, and make the similar made GNN to do the similar prediction task. And here, the comparison between the previous GNN and our GNN is shown as a function of time. So Poisson coefficients are much larger with our GNN network. So this was really striking for us. So we wrote a paper with Shimokawa sensei and Suzumura sensei at ICCG University of Tokyo. And the current status is much diverging in this field. So machine learning methods are additionally proposed afterwards. So the task of the GNN was supervised learning. So we are using the machine learning to fit the dynamics toward the structure. So in addition to the initial support vector machine, we have now graph neural networks. So later, the improved graph neural networks models have been proposed, and also relevant machine learning models are proposed, which exhibit similar degree of predictability as I will show in after the next slide. And also there appears unsupervised or self-supervised learning, which is very important for the task of for example clarifying what glasses are by. So there are similar models, but with the time because time is approaching, so I skip it. But there are actually similar models, important models are later proposed recently in the field. So I limit myself here to the GNN graph neural network related models here. So and I am listing the related models which is representing the states of the art at this moment. So here the three are GNNs, and I didn't mention, but actually, so this is a relatively large model in this field. So the number of model parameters are 10 to 6. So there are some similar variants of GNNs stemming from the DeepMind one, and the approach is different from each by each. And also there are small parameter models like small multi-layer perceptron models, which uses some physically informed, physics-informed descriptors, and also linear regression model based on some generalized physics modeling is introduced inside. And recently, because we wanted to unite these different approaches into one view, so we made a roadmap on machine learning classifications. So there are about 13 authors, and we have uploaded the preprint just probably yesterday. So you can have the access now to this article, preprint article, which dictates the current status of the machine learning classifications. So it dictates domain insights and also benchmarking. It's not a speed benchmark of the graph neural network processing, but that's the benchmarking of machine learning predictability of graph neural networks and other relevant machine learning models. So what we have now with these relevant models are, so here again, I am plotting as a function of time the Poisson correlation coefficient of different machine learning models when exhibiting different, for the task of predicting particle motion. So here the red dotted line is DeepMind GNN performance. And the other relevant models are, so Botan, the performance of Botan is drawn by yellow line. And also there are other three lines which are corresponding to, one is corresponding to another GNN and also other simpler models. So So here, what we see is they exhibit similar predictive performance, but there are some similar changes in the input information. So Bhutan is using a kind of thermal input directly obtained from the simulation trajectory. So thermal means this simple input. But other, if we do some pre-process, we apply pre-processing to each structure, input structure, then we can the other model people realize that they can raise the predictive performance of their models, and finally they get a similar performance as for over all the time scales in glassy relaxation. So GNNs are large models, so training takes, for example, some hours, typically 2 hours to 10 hours. But other models are simpler models takes a very small time, like order of 10 minutes or so. So even on CPUs. So this is a current situation. Maybe so input of the structure is actually influencing the predictive performance, but probably I do not have the time to address this in detail, so I should skip it. And but current status, summarizing the current status, in this year we have actually witnessed renewed state of the art for the task of predicting glassy dynamics. And there emerged new models along with 20 GNN models. Sorry, I didn't mention the GNN model details, but other models are actually, for example, using geometric GNNs or other variant GNNs, which are along with the trendy GNN modeling movement. And they have improved machine predictive ability. And by using pre-processed input structure, then various GNN models achieved similar performance to ours. But still, our model has the merit because the Bhutan still remains the best if we, for the task of using thermal input, I mean the direct trajectory data. So this is our model is, I realize, it is very good model actually. And we have recently put a preprint open for public, and we had actually made a benchmark, a systematic benchmark in detail by using my dataset. I mean the original dataset for Bhutan instead of the dataset by DeepMind. And for similar reasons, it will remain probably the standard in the field of this community in treating glasses in physics and material science field. Yeah, there would be very exciting applications in the future, but because time has expired, so I do not mention. I just, there are some 20 generative models, like diffusion models, and this might find some desired applications in near future. So I'm making this trial now, and also extension to other physical systems or more complex situations is now being tried by myself, which I hope I can present some results in this fiscal year, within this fiscal year. Thank you for your attention. I'm sorry for breaking the time limit.
Thank you very much. For any questions or comments? Okay, thank you very much again.
Very much.
Okay, so let's move to the final talk today. Another speaker, Dr. Shin Chai from Similar Research Laboratory from University of Oslo from Norway. And she and I are also a long-time friend and also the long-time collaborator. So recent several years. So I just remember, so we co-organized one workshop was in ICCG for 10 years. It's related to computational earth science. So now my colleague Shimokawa-san is taking over the job. I just remember that. Okay, so his title of talk is towards high performance unstructured mesh computations. Okay, so please join me to
Thank you very much, Kengo. I always enjoy your invitation, and thank you all for attending this seminar and staying to the last minute. Okay, so I'm going to talk about a classical topic in science computing. Here's the background. Modern processors are very good at crunching numbers, but the memory speed are lagging behind more and more. However, most of the scientific computations are memory traffic bound, so they rely on speed of memory. To make things even worse, that is some of the problems, they rely on solving realistic geometries using unstructured mesh. These will lead to sort of irregular memory accesses, so they make the situation even worse. So in this talk, I'm going to look at some aspects that we can do to improve the situation a little bit. I'm not claiming that we are solving the memory war problem for unstructured mesh computation, but some of the recent work that we have done, I believe, can help to make things a little bit better. So more specifically, I'm going to talk about 5 aspects that my team has worked on recently. The first thing is about reordering of mesh entities, having a purpose to improve memory usage. The second topic I'm going to talk about is to use automated code generation so that to make life easier to use GPU computing for the users. The third topic will be to look at a particular interesting topic. Can we use AI-specific processors, which are coming up more and more? Can we use them for traditional scientific computing? And the fourth topic is related to mesh partitioning. That is when you are using a large supercomputer, there you need to partition the problem first. And this is related to mesh partitioning if you're unstructured mesh, how we can improve mesh partition there. And finally, I'm going to touch upon a topic which is about understanding the overhead of point-to-point MPI communication in terms of parallel unstructured computation. And this is joint work with many of my team members at Siemens. So let me move on to the first topic, reordering of mesh entities for the purpose of improving memory performance. If you have unstructured mesh and you use some standard numerical methods like finite element or finite volume method to discretize the equation you are solving, you will end up with irregular memory access patterns. These are inevitable. These are bad for memory systems nowadays. In order to make things less severe, some reordering of the mesh might help. So I'm going to look at 2 situations where reordering the mesh actually can improve the performance of sparse computations. The first example is related to sparse matrix vector multiply, which is a well-known kernel in computational science. It's a sparse matrix A multiplied with a dense vector and produce another dense vector called Y. And you see here on top a code segment of OpenMP parallelized implementation of a sparse matrix vector multiply, where the matrix is stored in compressed sparse row format. You have different strategy to reorder the rows and columns in the A matrix with the purpose of improving memory performance, essentially by improving cache reuse on typical memory systems. And there are several strategies to reorder. There are reverse Kaplan-Meier, there are nested dissection, and also there are methods based on graph partition. So to convince you that actually it may pay off to reorder mesh entities, which equivalent to reorient and rows and columns in the sparse matrix. I have one example here of a sparse matrix. On the left is the sparse matrix where the entries are from the original mesh generator. So it's kind of a random ordering of the entries. And then the right picture shows, I think it's a reverse Katiyo-Maki reordered result of the rows and columns in the matrix. So you see the non-zeros are more densely moved to the diagonal. And because of that, we can see that the performance, here I'm showing the gigaflops performance of the SPMP result. Left, or the middle column is the performance using the original ordering of the matrix coming from the mesh generator. And then the right column is the performance result after applying reordering of the matrix. We can see that for all the 6 situations on 2 different hardware platforms, the improvement is quite noticeable, at least a factor of 3 improvement in this performance. Of course, reordering is still a big topic. It's not given what is the best reordering method. I would like to bring your attention to one very recent paper published 2 weeks ago at SC23. So they looked more systematically at different reordering methods applied to this SPMP problem. Moving on to the second example of reordering mesh entities, which benefit memory usage. I'm looking now at the assembly process in finite element computation. Here in the picture tries to show you the process. Essentially, what happens in finite element assembly is that you go through the elements one by one. For each element, you need to know the coordinates of the nodes that compose this element. This will be grabbed irregularly, randomly from memory. And then when these coordinates are known, you can do so-called local matrix computation, dense computation. And when this local matrix, dense matrix is computed, the values need to be spread out into the corresponding positions in this global sparse matrix. So the first step and the last step are very memory traffic intensive. In this context, we have found out that suitable reordering may help to improve the performance of this finite element assembly process. Specifically, what we have done is that, first of all, we reorder the vertices of the mesh using, for example, reverse Katiyo-Maki. And then based on that, we reorder the elements using a ascending lexicographic ordering. So we reorder 2 things, the vertices and the elements. And based on this reordering, we have measured the performance here. The numbers, the bigger, the better. Sorry, here. What I'm showing here is not the performance, it's the actual measured memory traffic using performance counters. The lower, the better. So the red box shows the original ordering from the mesh generator. If we use that to do the finite element computation, what is the measured memory traffic? And the blue blocks is the same memory traffic measurement, but when we reorder the mesh entities as I just described on the previous slide. As you can see, the improvement is quite substantial. And I can also mention that in this table, the second column is the theoretical best possible estimated memory traffic. So the blue box numbers are quite close, not exactly the same, but quite close to the theoretical minimum traffic because of the reordering I just mentioned. Moving on to the second topic, it's about using accelerators, not for memory traffic, but for the computing. So GPU computing is the thing I want to achieve because GPUs are often more powerful than the CPUs. However, GPU programming is not easy. Therefore, we looked at automated code generation to make this process less user demanding. Essentially, what you're combining is a high-level domain-specific language that the user is supposed to use, making the life very easy to describe the computation they want to do using this domain-specific language. And then behind the scene, there is a special compiler try to understand what the user has written in this high-level language, translate into low-level machine close implementation. In this regard, there is a framework called Phoenix. It's for finite element computations. It's a big project. Many partners, including Simula, have contributed to this big project. And one of the big features of this Phoenix framework is to use automated code generation. But until recently, the Phoenix code generator can only produce MPI's CPU code. It was not possible to offload the computation on the GPU. So recently, one of my students looked at how we can extend Phoenix, still using automated code generation, but to allow automatic offloading of computation to the GPU without the user having to do anything. The user can still write their computation in a high-level language that Phoenix uses, but behind the scene, now we are able to generate CUDA code. So the process is like this. So you have a partial differential equation you want to solve, and you write it into a so-called waveform, which is standard practice for finite element computation. That's the only thing the user needs to do. And then the user can write down this waveform in the so-called domain-specific language that Phoenix uses. Is embedded in Python. So the green box shows roughly what the user needs to write to describe the equation and also the details of finite element discretization. And then when this user code is done, the Phoenix compiler will take it over and translate into actual code. So the actual code is in the box down in the middle. So for example, we have extended the Phoenix compiler to be able to generate CUDA code. And when the CUDA code is generated, you can run it on GPUs, any GPUs, NVIDIA GPUs you want. Just to show that this auto-generated CUDA code can actually help to improve the performance of finite element computation, I'm showing here one table. It's about the performance achieved for the assembly process. So remember that for finite element computation, there are basically two big steps. The first step is the assembly process to construct the linear system. And the second step is to solve the linear system by direct solvers or iterative solvers. So here, this table is about the performance achieved for this assembly process. Again, I just want you to focus on the two boxes, the red and blue. And the red box is the performance achieved on a CPU, multi-core CPU machine. And then the blue box shows the performance achieved on a V100 GPU for the same mesh, same amount of computation. So here, the larger the numbers, the better. So as you can see that this auto-code generated CUDA code can actually outperform, as expected, the CPU performance by at least a factor of 3. And also for the entire computation, that's assembly plus here iterative linear solvers. So both parts together, total time measurement, translated into performance. Again, we can see the same feature or same trend, although the measurements are done on different CPUs and different GPUs. So still the conclusion is quite clear. With help of automated code generation, we have been able to auto-generate offloading of the GPU, offloading of the finite element computation on the GPUs without user having to change anything in their program, while achieving better performance because of GPU program. So the third topic I want to talk about is something which becomes very interesting lately, because there are more and more companies, startup companies, building processors which are specially designed for AI workload. However, I want to turn the table around and ask the question, can we use these AI-specific processors for some traditional computation? Of course, they are very good at running PyTorch, TensorFlow programs. We want to see also what they are good for computational science. In particular, the particular process I'm going to talk about today is the intelligent process units called IPUs from Graphcore, a company from UK. Each chip is massively parallel with 1,472 small cores. Each core has private SRAM memory. There's no shared memory between them, just private SRAM memory. But the aggregate memory bandwidth of all these 1,472 tiles is massive. However, it requires some special programming style, which is very special. You have to think about the computation as a graph, where the nodes are the small tasks to be executed, and the edge is about the data transfer between them. And so there you cannot specify explicit memory exchange, for example. You have to imply the data exchange through these edges in the graph. Originally, of course, it's designed for machine learning, but we have looked at using these graphical IPUs for other purposes, such as genome sequence alignment, such as graph analytics. And also, I'm going to show you on the next slide one application of cardiac simulation. So this is a simple cardiac simulator, which tries to understand the electrical behavior of the heart. Mathematically, it's a reaction diffusion problem in 3D on the realistic geometry. Therefore, unstructured mesh is required. If you use standard operator splitting for this problem, you get a so-called PDE part, a 3D diffusion equation, and then another part, which is a system of nonlinear ODEs on each mesh point. And this problem has been studied in collaboration also with Kango's group, thanks to this GHPC project that we have been running for at least 5-6 years. So we actually managed to port the simple cardiac simulator, as I just described on the previous slide, to run on this graphical IPUs with special programming. And we compare the performance of this graphical IPU for running this cardiac simulator towards the performance that we can obtain by running it on a running it on an NVIDIA A100 GPU. So this table shows the time measurement of the PDE part, the ODE part, and total time as a function of the number of IPUs or GPUs used. So here, the smaller the better. As we can observe, for the PDE part, thanks to this aggregate memory bandwidth of all these private SRAM memory of the tiny cores on the graphical IPU, actually it takes shorter time to do the PDE computation on the IPUs than on the GPUs. On the other hand, the ODE parts, which are very computation floating point intensive, the NVIDIA GPUs still have a clear performance upper hand for this part. If you're interested in details, there's a paper published earlier this year describing this work. Moving on to the fourth subject of my talk, I'm going to mention something we have done in regard to mesh partitioning. This is required if you want to do large-scale computation on a supercomputer. For solving a physics-based simulation problem, you have to partition the problem first. What is studied here is that if your numerical algorithm, the parallelized version of the numerical algorithm, is sensitive to how the mesh is partitioned, then you have to pay attention to how the mesh is partitioned, shortly speaking. That's what we are looking here. As the concrete example, we have looked at simulating the oil reservoir. It's three-phase flow in realistic geometries, looking at how mesh partitioning impacts the numerical performance or overall performance. So I will not dive into the numerical details, but it's a complicated nonlinear PDE system. Partitioning actually affects how the parallel preconditioner, which is necessary for the iterative solvers, how the parallel preconditioner works. So we have used one particular quantity, which is called the transmissibility between 2 and 2 neighboring cells in this mesh. This represents both geological property and also the shape of the cells. So this quantity you can compute on each interface between the neighbors, and we use this to partition the mesh in such a way. So to partition the mesh, traditionally is done by translating the mesh first as a graph, one-to-one match, and then you can choose to in the graph between the vertices, you can choose to give different weights to the edge. If you don't give any weight, treating every edge to be uniformly weighted, you're doing traditional mesh partitioning. But if you have different weights to the edge, according to some metric, then you are taking into the consideration of the connectivity between numerical connectivity between the vertices in the mesh. So what we have done here is that in addition to uniform weighting the edge, we have chosen two strategies. One is to use this transmissibility value as just described, use this value as the weight of the edge. Another strategy is to use the logarithm of the transmissibility value as the weight. The reason that we chosen logarithmic value of the transmissibility value is because the transmissibility value can vary a lot within an oil reservoir because of the very heterogeneous geological properties. So sometimes it's better to make the scale change small. So to see the effect, I have here showing one plot. That is the number of iterative iterations of the iterative solvers. How many iterations we need as function of the three different partitioning. The gray column is the standard uniform partitioning method, which is standard method for partitioning. The red column is the number of iterations associated with using transmissibility value as the edge weight, and the blue column is the result associated with using the logarithmic value of the transmissibility as the edge value. So see here, red is the best. The lower the iteration, the better. However, if you consider the amount of the communication, so because partitioning also has an effect on how much communication there will arise, as Rich just said, communication is unavoidable. Communication has a cost. The red column is the highest because in terms of overhead, communication overhead, the red partitioning is the worst. The gray is the best. That's the standard partitioning. The blue is second, not far from the gray. And if you combine all these three together, look at the total amount of computation time, then we see that the blue is the best. So that's an example showing that when you do mesh partitioning of unstructured mesh, if some of the numerical components, the behavior depends on how the mesh is partitioned, then you should consider this in your mesh partitioning in some way. Here is a paper that we have presented more results of this topic. Final topic for my talk is the detailed modeling of the MPI point-to-point communication cost. The reason that we did this work is because the interconnect on a supercomputer is heterogeneous. It has different levels within the socket, between the nodes, And between the nodes, there can be between, within a rack, between the racks, and so on. So there are different levels of communication, connectivity on the supercomputer. At the same time, if you're doing a parallel computation of unstructured mesh computation, after you do partitioning, the amount of data exchange between the neighbors, they are not constant. The messages can vary a lot in size. And also for each MPI process, how many neighbors it has to communicate also varies from process to process. So this communication connectivity is also heterogeneous. So we want to understand in a more precise fashion how costly the communication cost is for each and every MPI process, which is not studied by traditional state-of-the-art models. Just to show the limitation of state-of-the-art models, here is the so-called Poisson model, which is very classic. It describes just a pair of sender receiver, how much time it takes to send a message, given size of S, how many bytes S. If you know a latency value and bandwidth, and you can very accurately model a single message cost. Later on in 2016, Bill Graf and his co-authors have come up with this so-called max rate model, which targets situation that there are multiple messages as communicating at the same time. But the limitation is that all the messages are of the same size. And then they have this model where the bandwidth essentially depends on the number of messages being communicated. And this actual memory bandwidth, not memory but communication bandwidth looks like a roof line. It has a max rate, but before hitting the max rate, it grows linearly with the number of processes used. So this model, max rate model, is not very accurate. There are two reasons for that. The first reason is that it does not handle the situation of different size messages. It assumes same size message. That's one limitation. The second limitation is the simple roof line model used to describe the actual communication bandwidth is not very accurate in reality. So here on this plot, we're showing the actual measured bandwidth as number of competing messages in solid line. The red is the intra-socket, the blue is for inter-socket. The dotted lines are what the max rate model would say, where the solid lines are the actual measurement. So we see that these lines are not the same. So therefore, there's another inaccuracy in this max rate model. So what we have proved, we have proposed is a so-called staircase model. So these formulas are maybe difficult to understand. Let me just walk you through what we mean by this staircase model. So suppose you have, let's say, 5 messages you want to compete against each other. They are of different sizes. What we need to know first is to know on this given hardware, what is the obtainable communication bandwidth as the number of competing messages. You have we can run a simple ping-pong-like benchmark to measure these values. So these values are tableized in this, put into the upper right corner table. Once this is the information we need to know for this actual network we're using. And then you have on the lower right corner, the actual amount of communication between the pairs. With that, we can start to predict the time usage per process. So let's say you have 5 messages, they are of different size. The first thing we do is to sort them in increasing order. And then by logic, we say that the smallest message will finish first, the second smallest will finish second, and so on. So how do we decide when these messages complete? So to look at the first message, we use the memory bandwidth when 5 messages computing. So this last value in the table, we use that to estimate how much time the first message, the shortest message, will complete. And then when that's done, so all the other messages have been partially processed as well. So the remaining part of the second smallest message will be the smallest now, and that one will be using this memory bandwidth, where 4 messages are computing. So the second last entries in the table here will be used to estimate the remaining time of the second smallest message, and then you go on to the third smallest message, 4th smallest message, and finally the last one. So that's the staircase strategy that we have proposed. And we can extend this modeling strategy to handle mixture of different types of communication, like inter-socket mixed together. We have a way to say that the bandwidth there, how do we split the competing memory bandwidth of different types of communications without, I don't have time to go into details, but I'll show one paper that we have published that give you the details. And also it's possible to combine intra-node with inter-node communication cost. So here's the paper that we have detailed our new modeling strategy. And finally, just to convince you that we are able to predict quite accurately what's the communication cost for each and every MPI process. So here's a situation of, I believe, 64 MPI processes, and the number of messages and the size messages are all heterogeneous. And for each process, we have shown 3 measurements. The blue column is the actual time measurement per process. The green is what we predict using our staircase model. And the purple dots is what the max rate model, the state of art, would have predicted. So as you can see that the prediction accuracy, because of our new modeling strategy, is much better than state of the art. To conclude, I think I can mention 3 things. What I've just said is just some recent activities that we have done in order to make sparse computation coming from unstructured mesh computation more efficient, but they are definitely not optimized, not fully optimized. So more research is needed, I believe, in terms of both mesh reordering and mesh partitioning. We have only touched the surface of these 2 problems. More research is needed. Secondly, I think that automated code generation is a good approach for helping people to adopt new hardware like accelerators. There, new research also is needed. And finally, I think international collaborations are very important. So for Simula, we have benefited a lot from collaborating with University of Tokyo. And also also in the same subject, sparse computations from sparse instruction mesh computations, we have also benefited from a European collaboration, in particular the project so-called Sparse City. So there we have looked at different tools that are relevant for sparse computations on modern hardware. And finally, I can mention that one of my colleagues, together with 2 collaborators in Germany, they have looked at to use sector cache, which is a technique available from the Fujitsu A64FX processors, how the sector cache technology can be used to improve SPMB performance. So this is just one example showing that with proper research, we can improve the usage of a relatively new hardware even further. So with that, I thank you very much for your attention. Thank you very much.
Okay, so thank you very much. I think it's time to close. So I just summarize. Yes, so I have already shown this, right? So basically, so this is the final workshop for this project. So we started this one 2019 June, and it's a 5-year. More precisely, it's a 4 years and a 10-month project. So we still have 4 months. Yeah, it's a long project, but I felt it's very short. So yeah, one of the reasons is so we have a COVID, and so we have some just after the starting, we have a long time for just online for 3 years. So, but anyway, so we have I think we have very nice result in several parts. And so I just summarized my work this morning about the hardware and software, and also some future collaborations, and also new stages related to quantum computing. And I mentioned that we have 3 innovations for numerical algorithms and machine learning issues, and also the system software. And so each of the PI presented the result, and I hope so you enjoyed the presentations. And yeah, I really I'm really happy to the nice result from these 3 parts. And also extensions for the futures, and I mentioned about that. So our software to the quantum computers, and so this is a very nice so-called switching from the old project to the new project. And I'd like to thank all the co-PIs. Yeah, so they worked really hard and get a nice result. And thank you very much for your hard work. So especially I want to thank the 2 former postdocs, Shiba-san and Kawai-san. And I'm also happy, so both of them were promoted to the next position. So it's a very important issue for the postdocs in the this type of the project. And so yeah, thank you very much for your very hard work. And also I'd like to thank all the contributors and the international collaborators. And also I'd like to thank the 2 invited speakers. So again, I'd like to thank again. So we started discussion from tomorrow, and yesterday, sorry. And we have many insights from both of you. So yeah, I want to continue this discussion tomorrow. Okay. Yeah, thank you very much again. Okay, so as for the self-evaluation, which I promised this morning, and you can see, so you remember the presentation by Dr. Yashiro, and he mentioned 18 times faster by ensemble coupling. And I think this is one of the results which clears faster 10 times at the beginning of this project. Actually, I try to do that, the combination of the lower precision and the machine learning and some other issues. But so this improvement is just by algorithms. Okay? But if you apply the FP32, we can get the further improvement. And currently, my self evaluation is 80%. Okay? So 100% is impossible because I like 80% because we still have a 20% to improve, and we can do some future works. Okay? And I hope I can show you some another examples of the 10 times or something like that in SciPP 24 in Baltimore next year. Okay, thank you very much. And so thank you very much for all speakers and audience for a long time. So this is a very dense meeting, just half day, but I think it's a very nice discussions and very fruitful. And I get many new knowledge. Okay, so as I mentioned to both of you, I'm 61 years old, but I still have very exciting about getting a new insight and knowledge. And thank you very much for your attention and also coming. And, so I'd like to close this workshop. Okay, thank you very much.